All good? Can you hear me? Okay, I think let's get started. 31:15. Get rid of this annotate also. Like speaking there. Okay, today we're going to finish up the lectures we had on memory robustness, and we'll have Ismail and Nisa present some cutting edge research as we discussed yesterday. Ismail is going to talk about the ColumnDisturb and PuDHammer works that were published this year, respectively at Micro and ISCA. And Nisa is going to talk about side channel and covert channel attacks due to processing in memory, which was at DSN, and also similar attacks due to RowHammer defenses, which was published at Micro, and a solution to RowHammer, which is CoMeT, which is one of the principal solutions that people have devised. Probably we won't have more time to talk about other things. There are some plans if we have time, but please feel free to ask questions. We're going to talk about 5 cutting edge works after I finish the lecture. Does that sound good? Okay, great. Okay, now, oh, this didn't work. This is just an overview of what we covered. I'm going to go through this relatively quickly and then do some finalization. We're going to complain about reviewers a lot in this lecture. People who are, let's say, not very open-minded, not just reviewers, but there are such people. So get ready. Okay, so a lot of understanding. We talked about RowHammer that is developed in this sort of lab environment. So there's more to come, in my opinion. So if you're interested in doing research in this area, definitely talk with us. Ismail has been doing a lot of things in that lab over here, but not just Ismail, other people as well. So we've talked about RowHammer solutions. I will not go through them again. And we're going to see one more solution. And we're going to actually see in the paper some other solutions also for other read disturbance mechanisms. But this is a summary of the solutions. And we need more solutions, basically. We need better solutions in this direction, as we have discussed. And I think the solutions are all going to be intelligent controllers, as we have discussed. And industry is already adopting intelligent controller mechanisms like per-row activation counters. But there's more to come in this area for sure. So we're not done yet. And things are going to be harder and harder with issues like ColumnDisturb, for example. Or if you have processing using memory and you need to correct the different types of errors, including read disturbance errors, you need to think about how to correct these things. Okay, and we always ask a question, which is, can we do better? This is always the right question, actually. You can never go wrong with this question. You can ask it and you'll never go wrong. If you're actually someone who doesn't want to improve, you can always say, it's working okay, why change? We're going to see that also. But you've seen that before. Anyway, we'll see more. So that's why we also discuss different ways of partitioning work between DRAM and the memory controller, the self-managing DRAM work. You remember, again, I'm not going to go through this in detail. But I think to solve these problems, we need to really think out of the box and not think about immediate implementation and not think about the constraints of business as usual. Because business as usual really limits scientific progress. It is really designed for something else. Like if you're at a company, it's for making money, right? There's only one purpose company exists, to make money. That's it. Okay, but I think in research, we need to be much more open-minded. Basically, we should not be shackled by the standards that we talked about, right? The DRAM standard, for example, which you have seen in many lectures. If you're actually confining your solution to be compatible with the existing standard, your solution will definitely be suboptimal because standard is not designed for your solution, right? Your solution could be much better if you actually have a much more open exploration of the potential of the solution. And if you change the environment to actually make your solution better. And maybe there's a much better environment to operate in anyway, right? If the standard is very rigid, it's very hard to change things. This is actually a very general suggestion that I have in research, basically. If you confine your problem, limit it to a very small scope, you'll be very limited in what you can achieve in research because you're not thinking out of that box that you have holed into, right? For example, if you assume an existing ISA, an existing microarchitecture, and you want to change only one piece of that without changing the ISA, without changing the microarchitecture, you already limited yourself significantly, right? And it's a processor-centric design, let's say, yeah. So basically, it's good to have a broad perspective in research and say, what is the problem I'm trying to solve, and what is the best way of solving it, as opposed to I'm solving it under 200 different constraints and I have to satisfy all of them. Okay, the latter exploration of the problem is actually potentially a business type of exploration, right? Businesses are always under thousands of constraints and they have to solve the problem. As a result, what they do is very limited and incremental progress. Make sense? But sometimes in business also people say, okay, I'm going to scratch this thing and I'm going to create something new. And that's when big progress actually happens as well. Okay, and we've already discussed that you need to be resilient. You'll see more of that today, actually. And we also asked the question, basically, are we RowHammer free today? And we said, basically, there's a lot more to discover. And we discussed RowPress, for example. So RowPress is another read disturbance mechanism today. And we discussed in a little bit more depth, and you're going to read the paper. And you can also actually experiment with it. You can download the source code. It's very clean. It's a nice artifact, basically. And we've also seen this picture where we showed that the read disturbance vulnerability has become more than 100x times worse in terms of the number of activations to cause a bit flip over the course of 10 years, essentially. And we're marching toward a very small number. So basically, I think this sort of studies will continue to inspire different solutions, attacks, and vulnerability discoveries. And this was a summary paper. And again, I'm summarizing things. These two major directions still stand, understanding bit flips, and we're going to see actually cutting edge research on understanding bit flips and solving bit flips, but also not just bit flips, but also the interaction of processing in memory with bit flips and processing in memory with different kind of security mechanisms like side channels. Okay, I'm going to skip some of these because we've talked about this, but this is just to jog your memory about what we covered. Probably we will not get to covering ABACuS, which is another solution that we published last year, but we'll cover CoMeT first, right, Nisa? Okay, let's see if we get to it. If we get to it, Nisa will also present ABACuS. Okay, this is what Nisa will present. And there are other papers also that we're not going to cover, but you can see them. Okay, so there's more to come, basically. And I said yesterday that there's still a whole lot we do not know about DRAM. So we have this fascination with DRAM for some reason. It's been around for 60 years. It's still a very strong technology. And it's actually much stronger today than 10 years ago. Because 10 years ago, people were actually exploring other emerging technologies, which we will have a lecture on much more aggressively. But today, people have found out that actually DRAM is quite good, despite all of the problems, compared to other technologies. And maybe we should actually invest more in scaling it into the future with 3D structures, for example. Okay, so we're going to cover some of these. Actually, these are some of the papers that, two of the papers that Ismail is going to cover today. Okay, we also briefly discussed that emerging technologies are not as good in general, and also they have other problems. But it's good to invest. Again, as a researcher, you cannot say, okay, maybe I see sometimes emerging memory technology papers submitted to conference, and I'm a reviewer, and I'm very open-minded in general. I encourage people to work on this area. But sometimes the reviewers, annoyingly, say, Intel didn't develop phase change memory. Why are you working on it? To the author who has written a paper on this topic. Of course, the reviewer is anonymous. Authors don't know, right? This is anonymous blind review. I think this is very aggressive and annoying that reviewers do that. They should not do that because who cares, right? If Intel didn't manage to commercialize it, that has no implication on research, except people should know, perhaps, why this may have happened and be cognizant about it, but that shouldn't really hinder research. So I don't know, I think, but we need to somehow educate the reviewers to be more reasonable in general. And you will see more examples of this. These are not my papers that the reviewers commenting on, but some other people's papers. And I feel for the students who actually have done that research, because I think some of that research is really important. People should be working on emerging technologies, even if nobody else in the world is trying to develop products with them. because the goal of research is something different, generally, right? There are many types of research. I mean, we should be encouraging all types of research as opposed to destroying the research because the industry is not working on it. Makes sense, right? Actually, if the industry is not working on it, that's probably good to research. Okay, anyway, so this is why we built this sort of lab. And I think this actually doesn't exist in industry also, this sort of lab. So it's good, I'm proud of it, and people should actually invest in it if they have ideas to actually develop. Industry has different labs, but not this sort of lab in general. Okay, so we have also covered some papers that we're not going to cover in detail, but if you're interested, there's a wide range of literature in RowHammer spanning, not just RowHammer, but Disturbance, DRAM robustness, memory robustness in general, spanning devices to software. And I'm going to skip these because we have already covered this to get to the end. But this is, I think, a good summary of what we will discuss. This is a good prelude to what we will discuss soon. We also discussed briefly future memory robustness challenges. And I think intelligent memory controllers are not possible to avoid to make things robust. And when things scale to very smaller nodes, very small technology nodes, very small sizes, fundamentally, there are quantum-like effects that you run into, and there's noise, and you cannot control these easily, regardless of the technology you have. We have examined many technologies in memory, and all technologies have problems when they scale to the very small technology nodes. You need some intelligent controller to manage them. For example, even SRAM, we don't talk about SRAM a whole lot in this course, but main caches in processors, for example, buffers are made of SRAM. And people don't want SRAM to consume a lot of power, so they reduce the size of the cell as much as possible. And also they want to pack density as much as possible, right? And they also reduce the voltage. And if you do that now, SRAM becomes vulnerable to a lot of types of noise. And how do they solve this problem? Today, they have a lot of ECC, actually. There's a lot of error correction that happens in on-chip SRAMs today. And that's kind of an intelligent controller, right? They basically have a lot of ECC, and you try to correct errors. It's not really part of the memory. So the memory itself is actually vulnerable. It's not robust. You're protecting it with ECC. Whether or not that's a good solution, bad solution, that is the solution people employ today. And ECC on chip is not that bad. When you go to ECC on DRAM, it's much worse, actually. Okay, anyway, and we discussed this methodology. We should understand what's going on. We should model, we should architect, and we should design and test. Essentially, building this infrastructure helps all of those, and especially understanding and modeling. I'm going to skip these also because we have seen these. And finally, we discussed final thoughts on RowHammer. I've given you some stories on Byzantine failures, and also this work that was published in IEEE Security and Privacy in 2003, where the folks, the researchers introduced memory errors by putting a lamp next to memory and causing a lot of memory to actually have errors. That's a very creative research, actually. And I think people should publish that sort of research also. That may not be immediately applicable again, right? It's some creativity. They think, and this is the way we induce memory errors because we don't have any other way. And let's see how we can attack a system if you have that sort of thing. But RowHammer made it much easier. You don't need that lamp. You don't need that temperature increase. You can actually induce that memory error via software, simple software, user-level software. And we've discussed a retrospective of RowHammer, which I'm not going to repeat right now, but this really enabled a huge mindset shift in especially security researchers. And this enabled also discovery of other vulnerabilities. And there's a lot more to come, in my opinion, in other types of vulnerabilities that are at the core of hardware. If your hardware is really not robust and vulnerable, then you have a problem, basically, right? How do you make sure you can build a system that's robust from unreliable or vulnerable components? This is a good question to ask, basically. Okay, so we also concluded yesterday. I'm not going to do the conclusion again, but so this is where we ended up yesterday, actually. I'm going to briefly talk about logic because memory is vulnerable and memory scaling led to issues earlier than logic scaling because, for example, RowHammer was a big issue in 2013, 14, right? But logic scaling is also getting harder because as you reduce the size of any structure, in the end, this structure becomes more vulnerable to some sort of error, right? Some sort of error mechanism. And people have been also working on logic scaling and reducing the errors that happen in hardware logic. not necessarily memory structures, like adders, for example, right? Multipliers, pipeline, for example. And more recently, there's more, let's say, work in this area. It's not necessarily new, but there's a renewed interest in this area because large companies have figured out that, oh, they're seeing these logic errors in processors like CPUs in the field. And if you have 100,000 processors, these logic errors are happening maybe every day, every hour or so, because you have very large hardware. And if one of them fails, it'll affect your reliability, availability, and it depends on where the failure is, of course. So basically, data corruption happens in logic also, especially intermittent effects can cause silent data corruption. Intermittent means some error happens at some point under some conditions, but it may not be easily repeatable because you may not get to those conditions. And even if those conditions are satisfied, maybe you don't see it also because there's some flakiness that may happen. For example, you may have a very high temperature, and at that temperature, you may actually get some errors for some reason, right? So it's good to think about it that way. It may happen under some data patterns, and those data patterns, and maybe there's some voltage droop, for example, because you cannot perfectly supply voltages to our systems today. And if you have a voltage droop, for some reason, the circuit may run slower because you didn't supply enough voltage. So you cannot latch the correct data at the end of a pipeline stage, right? This may happen under certain conditions, under certain data patterns also, because you actually pushed your frequency too high potentially. And people have seen these errors actually, and these are hard to detect or replicate. They may or may not be exploitable as a security attack, but they certainly, if you get an error in a processor, they may actually affect your computation. Okay, and these are some papers that were written on this topic by Facebook and Google, and they actually made a big deal of it, let's say, even though these issues were studied a lot in the past years. I'm going to show you some of the papers that we have done in 2000s, late 2000s on this topic. But they made a big deal of it because they actually thought that this sort of error essentially happens a lot in their data center due to the law of large numbers, right? Because they have a lot of machines. So the first one, for example, has a story about how one error affects the software. You may want to take a look at that database. And the other ones actually has also essentially a talk. You can actually watch it on YouTube. But basically, they have a new problem. They actually acknowledge that that's not necessarily new, but they see it in the field, apparently. Cores that disobey instructions. I guess that's the fancy Google way of talking about things. Fundamentally, it's an error, right? Disobey instructions. I don't know why people like anthropomorphizing things. Core is not disobeying instructions. Core is an error. It's not really explicitly disobeying, right? Anyway, people like advertising things. Anyway, but there's a good part of this paper also, which is they show that there are some CPU cores that repeatedly, but not always, miscalculate certain computations without giving any obvious signal. Again, they term this mercurial cores, another interesting advertising term, and call it corrupt execution errors. But basically, if you cut through the, let's say, language, in the end, there are silicon defects, not soft errors, basically. They say this is because the circuit is not designed to be reliable under some conditions, and under those conditions, this error happens, and they see it in the field. Okay? Again, I would recommend reading this paper. If you've done a lot of fundamental work on dependable systems, you would not like their terminology. You've seen an example of that, basically. Okay, I wouldn't call this a mercurial core. It's basically a failure mechanism that happens and you get an error in the end. Okay, but sometimes system level people like amplifying things. Okay, but there are more recent works actually. There's a nice work by Alibaba where they analyze some of these silent data corruptions. It's an SOSP paper, I think, in 2023. You might want to take a look at why that's happening. And there's a very nice work actually by Google and University of Chicago where they actually look at why these silent data corruptions may be happening in machine learning accelerators like systolic arrays like TPU. And they also identify what's the effect of these silent data corruptions on software like training, machine learning training. And they actually try to find mechanisms to fix these when they happen. So I'd recommend actually these two papers a lot. The other two papers are a little bit, let's say, very high level, but these are more scientific, if that's the right word. They actually do proper analysis of these things. Any questions? It's fascinating, right? If you have millions of computers, actually, you'll see a lot of hardware failing. And you can have a lot of data for analysis, and that's what Alibaba has done in their analysis. But there's more to do in this area. I think there's more analysis that needs to be done. Yeah, it's also good to analyze some of the memory errors as well, because they also happen a lot. Okay, so how do you detect hardware errors? So the reason I'm criticizing some of the terminology is there's a very established field of dependable computing that is out there for 60, 70 years, maybe more. And people have done work in certainly identifying defects and fixing them. And we have done some work actually on some soft errors that may happen because you have some hardware defect that is exercised under some condition, maybe some voltage conditions, maybe some corner case, maybe some data pattern. So if you actually have mechanisms to test the hardware once in a while, the idea in this work is you do online testing of hardware, different parts of hardware, different cores, for example. You run essentially some testing programs that go through different parts of the hardware once in a while and check whether the logic is working correctly under different data patterns, under different conditions. And if you keep doing that, you can discover some of these errors early before your program actually experiences it. That's the idea over here. And we actually thought that giving this mechanism to the software is a good idea. Software can be thought of firmware, right? Operating system, for example. And the operating system can run these tests once in a while in different components of the hardware. And this is actually one of the solutions that is employed to fix or detect early the silent data corruption errors in the field today. So people are actually adopting these techniques that are old because they're actually seeing these errors right now. So it's good to work on some mechanisms that are actually not happening at the time. When we actually did this work, basically, the goal was not to show that the problem is happening right now, right? But the problem may happen in the future because we're clearly scaling the logic. And eventually, you may get into a position where you actually get these errors, right? So it's good to look into the future when you're doing research. Okay, that's one work. This is another work that we did where actually, here we did not look at hardware defects that happen under some conditions. This is really hardware bugs, meaning someone actually wrote RTL and the RTL is wrong. Can you actually identify this and fix it in the field? Because the wrong RTL may have slipped into the field. That's basically a bug. It's not a defect in that case, because it's really potentially a logical bug, for example, that you have. And if you're interested in this, I like this sort of work. There isn't that much work that you see in this area today because it's a very dirty area. We did analyze a lot of the hardware bugs that in an open source code at the time. We're talking about 2007 or so. There were open source codes at that time, like OpenSpark. It was not as highly, let's say, advertised as RISC-V, but they were good open source pioneers, let's say. But in the end, they actually, you can actually analyze that code and figure out what sort of errors people have corrected, meaning RTL designers. And you can actually use those errors that are corrected by RTL designers to design a mechanism that could potentially correct those errors in the field when they're discovered in the field, assuming the hardware designer didn't have time to correct it. So it's good to think about that. So this way you can actually ship something that is not completely working, but maybe debug it over time, right? So it's good to think about that. So if you're having this sort of debugging mechanisms actually is very useful in the field because who knows what kind of bugs exist. Actually, if you look at microprocessor errata today, there are hundreds of errors that are known in microprocessors that are not fixed. And you can read these in Intel, for example, or AMD. They will tell you in a vague way under what conditions these errors happen. But of course, they don't tell you enough because they don't want you to replicate these errors. But they want to cover themselves because, oh, we know this bug, right? But we're not fixing it because it's too whatever. Okay, so it's good to think about this. Then we've also done more work on scheduling these online self-tests that I mentioned in the operating system so that you can actually get good coverage of errors and also without high performance impact, because if you're actually always testing your hardware, then what are you don't have time to run the real workload, right? So we don't want to actually disturb the real workload much. And we've also looked at online self-testing of on-core structures. So you can test processor structures. That's interesting. But you should also test all of the other parts of the if in fact the hairy parts of the machine, which is on core and memory controllers, for example, to make sure that they're all working correctly. Okay, and there's more, but I'm not going to talk about that. So there's work in this area, and this is a renewed area. There's more work currently, but I didn't have time to add more work. Essentially, there's more work in this area that's happening. And the difference right now is when we were doing this work, there was not a lot of evidence that it was a huge problem. But today, it's a much bigger problem because of the scale at which we're operating these systems, plus the small scale at which to which transistors and hardware structures have scaled into. So the takeaway is both memory and logic areas will become worse with technology scaling. We looked at memory technology scaling, and I've given you a glimpse of the logic technology scaling as well. And these areas will create worse robustness problems. And essentially, this is my takeaway. We cannot afford to ignore data corruption in the end. And it's good that large companies are figuring that out right now. Okay, any questions? Thoughts? Otherwise, we're going to have some fun now. Okay. So let's talk about, we've talked about some review examples, right, in earlier lectures. I want to talk about the RowHammer review example because I think there are a lot of interesting lessons over here, for both people who review papers, scientific reviewers, and also people who do science, who want to advance things. And these are sometimes at odds with each other. People who want to advance science are opposed by hard-headed reviewers that don't necessarily see the value of what is done. So this is the original RowHammer paper that you have read. How many people have read this so far? Yeah, okay. Well, I think Ismail has read this 10 times or so. No? Okay. Okay, maybe once was enough. Ismail is smart. Okay. So basically, you know what this is basically. You know that it had led to a large body of work, and it had led to a large industrial effort. It had changed, it had enabled perhaps the biggest change that has happened in DRAM over the course of 2 or 3 decades, maybe more. I don't know. But DRAM manufacturers have not added so much hardware into their DRAM chips in the past. So work building on RowHammer continues clearly, and dedicated RowHammer sessions and top conferences you have seen. Initially, it was dismissed by some reviewers. And let's analyze why it was dismissed. It was rejected from the Micro 2013 conference. So it could have been published actually, like technically 1 calendar year earlier, right? If you care about that. Some people do. In the end, one should care about the impact of the work, but it's kind of annoying that a good paper gets rejected, right? You should be annoyed, but you should be resilient also. Okay, so these are the reviews. You can see that it was submitted on 31st of May, 2013. And you can see that these are the anonymous reviewers who have reviewed the paper. They don't know our identities also. Maybe they can guess, I don't know. But nobody's supposed to know each other's identities. And you can see the reviewers, like 5 is a great score, 4 is a good score. 1, basically this paper should be accepted over my dead body. And 2 is close to that, let's say. Yeah. Sometimes people think over my dead body, but they give 2 so that they're not seen, let's say, as terrible people, whatever. But 5 and 4 is usually difficult to get. So you can see that there's a pretty divergent set of reviews. 2 accepts and 4 rejects. And this paper was rejected in the end. But let's take a look at the reasons. So this is a very strong reject, as you can see. It's over my dead body. Reject. Many results and observations, strengths, insights on how the whatever may happen. It's not a perfect review, as you can see. But this is the rejection reason, main one. Basically, the paper shows that disturbance may happen in DRAM array. Authors don't show it can be an issue in realistic DRAM usage scenario. What does this mean? Basically, they think the security issue is not realistic. Even though we show with a user level program that this can happen, they're not convinced that this happens in real programs. And that's their reason for reject, because they don't think this is a big deal. It's interesting, right? Okay, let's see. I found the paper well written and organized, easy to understand. The topic is interesting and relevant. However, I'm not fully convinced that the disturbance problem is going to be an issue in a realistic DRAM usage scenario, main memory with caches. We've actually shown that you can bypass caches. So there's a user level program that contradicts what they say, but what they really mean is results are not, what they really mean is basically they, let me see. Okay, let me read it first. Overall, the work presented, the experimentation, and the results are not enough to justify claim that disturbance may be an issue for future systems and that microarchitectural solutions are required. That's interesting, right? People are developing many solutions these days. There's a microarchitectural solution in DRAM. Okay, I really encourage the authors to address this issue, to run with a new set of experiments. If the results are positive, the work is great and will be easily accepted in a top-notch conference. Test scenario in the paper, open, read, close a row many times consecutively that is used to create disturbance is not likely to show up in a realistic usage scenario. Basically, they want a real application doing this, right? Which is very, very hard to do. The first work where the real application did this was this Microsoft paper, Moisey Prime, that was published in 2022. Okay, so sometimes reviewers, let's say, have delusions that something is easy to do. But I think the bigger issue with this review is they dismiss a really important case because they personally, subjectively think it's not important, right? So they seem to know the whole world and they decide security is not important. This is not a scenario that we should worry about. But clearly security people didn't think so after the paper was published. Okay, so it's good to think about basically. And we basically rebutted this way, but they didn't buy our rebuttal apparently. Malicious workloads and pathological access patterns can bypass trash to cache and access the same DRAM row a very large number of times. While these workloads may not be common, they are just as real. That was our response to this person, but they didn't buy it. So in the process, usually what happens is they ask you questions and you have some time to respond. And I think this was our well-crafted response, but apparently it's not real for them, right? It's real. This damn thing runs on a real machine. You get these errors. What else do you want, right? Okay, it's good to think about this, as a reviewer, also as a person who receives the review. Okay, so reviewer A also wants some demands. This is also interesting. To make sure that correct information and messages are given to the research community, it would be good if the conclusions drawn in the paper were verified with the actual DRAM manufacturers. There's a huge conflict of interest here. Although I see that it can be difficult to do. Okay, thank you for seeing that. Yeah, manufacturers don't want to even talk about it. And second, what makes you think that we didn't try this? Again, the reviewer is assuming that maybe we didn't try this, or we should write about it. And what makes you think that the manufacturers will allow to write something about this, right? So you see, I think there's a very warped way of doing reviews, and don't do reviews this way. My goal is to educate the community to actually not do bad reviews like this, because if you see a paper, you should be much more open-minded, right? You cannot verify many things with the manufacturers today or anytime. Okay, this is fun. We can ask questions also. Okay, so this is actually another interesting reason for rejection. This is an excellent test methodology paper, but there's no microarchitectural or architectural content. They didn't think our solutions were microarchitectural, like para solution. It's actually microarchitectural, right? Okay, my primary concern with this paper is that it doesn't have microarchitectural content and it may not spur on future work. Okay, that's also interesting. Okay, let's see. This is an extremely well-written analysis of DRAM behavior, and the authors are to be commended on establishing a robust and flexible characterization platform methodology. This should be accepted based on that only. But as you can see, this person gave a weak reject. And I guess let's read it. Why not, right? That being said, disturb errors have occurred repeatedly over the course of DRAM's history, which the authors do acknowledge. History has shown that particular disturbances, particular hammer errors, are short-lived and are quickly solved by DRAM manufacturers. Historically, once these types of errors occur at a particular lithography node DRAM density, they must be solved by the DRAM manufacturers. Because even if a solution for a systemic problem could be asserted for particular markets, blah, blah, there will always be significant DRAM chip volume in single-piece applications where complex architectural solutions aren't an option. Again, opinion, a lot of opinion. I have my opinions also. I don't agree necessarily over here, but in the end, the authors have identified a contemporary disturb sensitivity in DRAMs, but as non-technologists, I don't know what that means, our community can generally only observe, not correct such problems. And this person is a self-proclaimed expert. If I were an expert, I would solve problems. Okay, sorry. We said that we're going to have fun, right? But you can see that this is actually a really weird thing to say in a review, right? Basically, don't write this paper because we cannot solve these problems. That's what this boils down to. It's a great paper, but don't write it because we cannot solve it. Weak reject. What kind of warped mindset is this? Sorry. I think we should send some of these reviewers to psychiatrists, you know. Okay, another reject. Let's take a look at this one. Nothing new in RowHammer. Okay, the mechanism investigated by the authors is one of many well-known disturb mechanisms. The paper does not discuss the root causes to sufficient depth and the importance of this mechanism compared to others. Overall, the length of the sections restating no information is much too long in relation to new work. This guy didn't want to read the paper, as you can see. Insignificant novelty. Virtually all of the ideas are published or known. It's interesting, right? Okay, so basically, nothing new in RowHammer. And this is a very strong reject, as you can see, right? Or my dead body type of reject. And nothing useful. This is not useless feedback for authors, right? If you read this. We of course rebutted it, and there's a rebuttal, but they didn't really, it's not clear if they read it. But it's good to think about this basically. There's a system that's in place. You try to do as best as possible great science, and then you get this. And I don't know how you characterize it, but this is a crap review from my characterization. It's very bad because it doesn't give me anything useful, right? It basically says it's not novel, but that's not true. It says it doesn't discuss the root causes, but that's not the goal of the paper. We actually do discuss the root causes, and we say that we actually talk with the manufacturers about the root causes, and these are the things, but that's not the goal of the paper. The goal of the paper is to demonstrate that this problem exists in many chips. You can induce these bit flips and characterize many well-known mechanisms, right? So basically, this guy has a problem. He or she wants us to write a different paper that's more novel and forget about RowHammer. We don't know why, because we don't know who is reviewing it. Maybe they're a DRAM manufacturer who don't want people to write papers on this topic, right? It's good to think about this, right? Or maybe they're a competitor who is jealous because if you write this paper, they cannot write the paper. It's good to think about these issues, you know, because these issues affect science a lot these days. I'm going to show you some other things later on. Is it fun? Okay, so this is ISCA submission. So we basically said, okay, these guys didn't like the paper. We're going to improve it. We did improve it. Nothing fundamental has changed in the paper. I think in micro submission, we had maybe 90 chips, 90 modules tested. In ISCA, we made it 130 or so, 129. And then we improved the writing, we improved the solutions, etc. We sent the paper to ISCA, and these are the reviews we got. The scale is different. I think there was 8 is award quality, and then 7, 6, 7. So that's good. Now we have 4 people who are actually pretty positive, but you still have 2 people that are pretty negative, right? 2 is over my dead body. 1 is actually over my family's dead body also, probably. I don't know. Yeah. So basically, these reviewers. Let's take a look at these 2 reviewers. Of course, the positive reviewers are positive, and they champion the paper, and it got in, apparently. I don't know. That's what happened, probably. But let's take a look at these interesting reviews. So this is very interesting. Reviewer D, basically. This is a known problem to the DRAM circuit community. There's no paper on that. How is the known problem if there's no paper, basically? The first one asserts as the known problem without showing a paper. Okay, they didn't show a paper. Maybe 2 is basically the backup of 1, but let's take a look at what 2 is. What you demonstrate in this paper is so-called DRAM row hammering issue. You can even find a YouTube video showing this. Very scientific. Okay, you go to the YouTube video, which doesn't exist anymore. It's not an archival thing, YouTube, by the way. YouTube may die and all of our lectures will be gone, including this RowHammer lecture that was deleted. It's not a lecture, it's a 3-minute video. And this guy is equating that 3-minute video with all of the scientific contribution we made in that paper. Besides, I actually know that video. It's only 10 seconds of it is about RowHammer. It's by someone called Mark Lantane, who actually did things in RowHammer. And these guys were developing testers, DRAM testers. And RowHammering is really something that they tried to test for in their testers, but they didn't have a very good understanding. And they actually described this video partially was taken in October 2013 in the MEMCON conference in Santa Clara. And I talked to these guys, actually. I said that we were actually doing work in this area, etc. But they didn't really discuss anything. They basically, in the video, which you cannot find anymore, sorry. I wish you could find, but you can try, I guess. For 10 seconds, they say, oh, our tester can test hammering things also. That's it. So the smart ass reviewer says, okay, it's great. Reject, because I have this YouTube video. If you get this sort of review, what should you think as an author? Anybody? To think this is a stupid reviewer. That's what I would think, you know? But not all students think that way. Sometimes they're affected pretty heavily. So don't get affected, basically. My suggestion is be resilient. This is a stupid review. Sorry. Yes, please. Well, row hammering issue, as I said, this was communicated to Intel at some point, and there's a poor Intel engineer who spent 1 year of his life to figure out what was going on. And he figured it out in 2011 or so, and we started working on this in 2012. So it was known, but it was not well known. It was not characterized to the extent that we characterize it, for sure. Right? And also, this video was uploaded in October or 2013, late 2013, and our paper was rejected from the previous conference much earlier. So if they accepted our paper, this video would not have been there, right? So you see. So known doesn't mean that it's well known. Maybe a few people know about it and they try to be hush-hush about it. Also, it doesn't mean that it's scientifically characterized at all. Right? So equating a scientific work that is as strong as this one, and I watch for it, and I think a lot of people would watch for it right now after the paper is published, with a video is really malicious, almost. Yeah. I mean, people do testers for everything, right? Like even after we wrote our paper, the Passmark software developed their testers. We covered it in a few lectures ago, and their testing mechanism was not good enough. So they couldn't cover all of the errors. Okay, so I'm going to move on, but the architectural contribution of the study is too insignificant. So you can belittle a lot of things, as you can see as a reviewer. Partially, I think I will get to, but this is because reviewers don't have any accountability, right? If the reviewer name was known, if the reviewer's affiliation was known, maybe they will have a little bit more accountability, and they would be a little bit more careful in evaluating work. Okay, so let's see. Okay, there are some odd questions also, but I'm not going to cover that. Like, there are other sources of disturbance errors. How can you guarantee the errors observed by you are not from such errors? Okay, anyway, we respond to it in the rebuttal. You can read. I think I copied some of them. Okay, whatever. This is a well-known problem to the DRAM community, so no novelty in there. In DRAM community, people use. Okay, blah blah. Okay, this is also interesting. I like this one actually even more, maybe. I think basically the relevance of this paper to ISCA. I feel that this paper is more appropriate to conferences like International Test Conference or VLSI Test Symposium, or Dependable Systems and Networks at most. The word choice at most is very interesting. What does it tell you about this reviewer? We're going to do some psychological analysis. They basically say, I'm a better guy than people who publish in these conferences. I'm a computer architect. Come on, go to ITC, VLSI Test Symposium, DSN, but don't bother me. I'm the king, right? So it's good to think about this, you know. But you do get this sort of reviews. This is why we're discussing this, because this is a very bad way of doing science, in my opinion. Okay, I'm not even sure. Okay, read more. It's very weak, blah, blah, blah. I'm not even sure this can be published to these venues, since it's a well-known problem. So if you're doing reviews, please don't do these. These are really, really bad, because this is really not helping anything, you know. Okay, anyway, we have some rebuttals, but I'm not going to go through this. Another reviewer said the same thing. RowHammering appears to be well known, and solutions have already been proposed by industry to address this issue. We actually cite the patents that are out there. So clear there were patent applications by Intel, and we cite them in the paper. But again, doesn't matter. Some things are wrong over here, actually. The paper only provides a qualitative analysis of solutions to the problem. That's not true. We quantitatively analyzed para-solution, which is actually later employed by industry. And para-solution was not a solution that anybody thought about until this paper. That's good to think about this, right? People try to build it up. So the question is, I mean, this is a weak projectile. It's not as bad as or my dead body. But again, you can see my overall feeling is that while the reliability characterization is important and interesting, a better target audience for the characterization work would be in a testing reliability venue. So you should not bother me. Okay, and they want the paper to be written in a different way. Okay, you can see the rebuttal, but I'm not going to talk about that. So can we do better, basically? Why am I telling you all of this? I think as evaluators of scientific work, we can do much better, right? Because the goal of science is to advance science. And people should be fair, and partly because they don't know it all. And that's true in everything, actually. We do not know it all in every interaction, right? We don't know the past, present, future, right? And people should be open-minded. Again, we don't know it all, right? The claim that this is done is a very strong claim, unless there's something, a scientific work that's out there that actually covers the contributions of the work, right? That's really important to think about. Again, people should be accepting of different, diverse research methods. There's no single way of doing research or writing papers. They cannot say, oh, this is not material for ISCA. Clearly, there's a lot of RowHammer and RowPress papers on ISCA right now, read disturbance papers, ISCA, micro HPC ASPLOS. Also DSN, VLSI, ITC, and also device level. Doesn't matter that it should be constrained to one community, because the problem, as we argued in this paper, is actually it should be solved architecturally. That's what we contended for. People should be more constructive, not destructive, and also accept more, in my opinion. I mean, of course, they should be rigorous about the scientific things, but they should not try to destroy. I would argue that some of the comments you've seen over there are to destroy, not to help the authors. And actually, sometimes it does destroy students. You know, students get affected by this. For me, it's okay. I have a thick skin. I will say this is a stupid reviewer because I don't agree. And I'm not even sure this reviewer is an expert, even though they claim they're an expert, because an expert, at least a reasonable expert, would not do this sort of thing, right? Because their goal should be really advancing science as opposed to trying to destroy a good paper. And double standards are also very important because everybody has biases on everything, including myself. But people actually don't suppress their biases or identify their biases, right? They basically sometimes get carried away, even though they may not be malicious. They could be erroneous. We've talked about Byzantine failures, right? Meaning they get carried away in their thinking that that's the only thinking that they have, and that's the only way something should happen. And once reviewers get into that mode, they can actually destroy good scientific work to be not accepted. Okay, so this is really important, actually. And there's also double standards like conflict of interest, right? Those are actually very, very hard to detect sometimes. Clearly, a person from industry has a conflict of interest because, especially from those companies that manufacture these chips. And if they review this paper, in general, they would not want to accept it, right? This sort of thing. So it's good to think about this, basically. And those conflict of interest, unfortunately, are not monitored. And they cannot be visible because we don't know the authors, we don't know the reviewers, etc. So there's also non-transparency in the system, which is not very good. But in the end, scientific progress either gets blocked or delayed for non-reasons. And students' mental health gets hit. I've seen that. And also, some students actually don't want to do research anymore. Maybe this is the goal of some of the poor scientists, right? They want good people not to do research so that they can do their poor research. Sorry, I'm very cynical, but there's a very good truth behind this. And these issues need to be discussed, you know. Okay, so if your goal is to advance science, my best advice is really to get the best out of their use and ignore the crap. Because you will get a lot of crap like this. It's becoming worse, actually, with AI. People are putting their review papers and letting ChatGPT review the paper and then pasting the review in the review form. We've seen that, and we've gotten reviews for other papers that we didn't submit to because they forgot to clear the memory of ChatGPT, you know. So this sort of thing also happens these days. So you need to be really resilient in the end. So there's actually this nice article out of all places from Wall Street Journal. Wall Street Journal is not the bastion of science, let's say, but but in the end, they have written this basically could Einstein get published today? Right? It's going to be very difficult for this poor guy to get published. Good thing he lived much earlier. Sorry, it's not to discourage you guys, but this is to encourage you guys that you should actually. So Einstein, for example, when he came to the US, went to the US. I'm not in the US right now. Okay, maybe mentally I am, but physically not. But anyway, when he went to the US, he sent his article that he wrote to a journal. And he basically sent it, and eventually he got some reviews. And he was furious. He basically said, I sent you my article for you to publish it. I didn't ask you to send it to someone else to review it. So he was annoyed. And he basically took the article and sent it somewhere else in the end. But also he actually addressed some of the comments, apparently, according to the stories. So he believed in his research, and he actually was confident, but he also addressed the good comments, apparently. So maybe we have become very bureaucratic. And this article actually talks about that. It's not just less room for individual style, but it's very bureaucratic way of doing science and reviewing science. Humans are great at creating bureaucracies, and they've created a bureaucracy of science also. The goal is really advanced science, and we're kind of slowing it down. So this is a recommended book. Have you seen this book before? Okay, this is a beautiful book on computer systems performance analysis, scheduling theory, etc. I'd recommend having a copy of it, actually. It's relatively old, but it's very nice, actually. And I like this page from this book that basically covers some rat holes and the reasons for people to reject things. Basically, this book says that you can reject anything based on workload, metrics, configuration, and detail. And these are respectively different size rat holes. So you can say workload is not good, and that's a big rat hole. You can say metrics are not good, configuration is not good, detail is not good. Every idea you can actually attack in the end. If your goal is to attack ideas, this is a great picture to put next to you. So basically, let's read this actually. This says, even if the performance analysis correctly done and presented, it may not be enough to persuade your audience, the decision makers, or the reviewers in this case, to follow your recommendations to get your paper accepted, for example. The list shown in box 10.2, which is this list, which we're going to get to, is a compilation of reasons for rejection heard at various performance analysis presentations. You can use the list by presenting it immediately and pointing out that the reason for rejection is not new and that the analysis deserves more consideration. Also, the list is helpful in getting the competing proposals rejected. It's a tongue-in-cheek thing. So, okay, let's read a little bit more. There is no clear end of an analysis. That's absolutely true. Any analysis can be rejected simply on the grounds that the problem needs more analysis. Right? You've seen some examples of this from the reviewers, right? You haven't gotten into the root causes as much as I want. You haven't really showed that this is a real problem in real workloads. More analysis, basically. You need more analysis. When does it end? This is the first reason listed in box 10.2. The second most common reason for rejection of an analysis and for endless debate is workload, which is here. Since workloads are always based on past measurements, their applicability to the current or future environment can always be questioned. Actually, workload is one of the 4 areas of discussion that lead a performance presentation into an endless debate. That's absolutely true. These days, also, of course, everybody wants to accelerate matrix multiplication. So if you do any other workload than matrix multiplication, you get rejected. You're doing genomics, who cares, right? It's good to think about that. Workload could be used that way or that way also. These rat holes and their relative size in terms of time consumed are shown in this figure over here. Presenting this cartoon at the beginning of a presentation helps to avoid these areas. Good luck. You're not going to avoid these areas, basically. But it's good to see this. And Rod Jain, who's the author of this paper, has a very good sense of, let's say, keen sense of understanding of maybe human psychology and behavior. So I like this, basically. So you can see reasons for not accepting the results of an analysis. The top one is this needs more analysis. You need a better understanding of workload, blah, 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 blah. I like the last one a lot. Actually, that's not the last one. 23, this impacts hardware. This is the software person's thinking, of course, right? And actually, if you send something to a software conference, you will get this. This impacts hardware, don't bother me. Similar to the other guy who was saying, this is about characterization, send it to ITC at most. I'm not even sure if they will accept it, Maybe you should not be doing, maybe you should go to your corner and do nothing in your life. That's what they're suggesting, basically. Okay, I like this last one. Why change? It's working okay. Right? There's no better way. And this actually happens a lot in companies, for example, institutions. Oh, you get into this is the business as usual mindset, basically. Oh, we have a good way of designing processors. Let's keep doing the incremental thing, and it's working okay. We're making money. This happens in any institution. It happens in universities also, right? Why change? It's working okay. Our system of education is the best in the world. Why do we try different ways of doing education, right? Why do we live stream our courses? You see where this goes? There's no innovation that happens if you actually get into this mindset that's business as usual. It's a life thing. This is actually about life, I think. Okay, so I think given all of this, what are the suggestions for people like you? I think we should still address feedback, take things positively as much as possible. They can be helpful, but of course, feedback is not always right, clearly, right? And you should believe in the research you're doing, unless it's wrong. When it's wrong, you should accept that it's wrong, and you should fix it. But if it's not wrong, and if it's the right thing to do, you need to apply corrections. And sometimes you need to ignore some of the reviewers, because that's the same. That's the best for sanity, Otherwise, if you keep thinking about this reviewer who says you should not do anything in life, because I'm not sure if this lowly conference would accept it, you will not do anything in life, right? Go become a barista or something, they're saying. Okay, anyway, barista is good, actually. I don't have a problem, but that's a different kind of thing. We didn't submit this paper so that we can become a barista somewhere, right? We submitted this paper so that you can provide us a scientific good review, and you didn't satisfy that simple requirement. Okay, basically, do not let rejection derail you. Be ready for it, because it's going to happen. It's going to happen in the academic world. It's going to happen in industry world. It's going to happen everywhere you go. This is actually a very good characteristic to build, a thick skin. And many top works were rejected before, actually. And when I have my students, when I have some students who actually have papers rejected, I point them to these links. And I tell them, I hope you join these folks, because these folks are actually who had papers rejected, and those papers actually went on to win the Nobel Prize. And there are many examples of this. In fact, there's actually much worse examples, which, okay, I'm not going to talk about that right now, but maybe in a later lecture. Even if you have a Nobel Prize winning discovery that may not be immediately acknowledged, there may be people who are actually out there to get you, despite the scientific evidence. And there have been discoveries like that. Dan Shechtman, for example, he actually made a discovery of nanocrystals, and nobody believed him. And he had a very difficult time for publishing that work. And he was actually almost persecuted by another Nobel Prize winner, whom I'm not going to name over here. But I guess after that person died, he actually won the Nobel Prize. So it's good to think about that, So you're not alone in the end. There are personality effects that go into this also. So there may be really brilliant people actually who don't want you to succeed for some reason. You can read about this. It's public. But some of these other things may not be public. Okay. Anyway, that's why you should believe in it. So if you look at Shechtman's interviews, you will see that he believes in what he does, and he actually pushed despite all of those difficulties that he had gone through. Okay, let's take a look at reviews after the paper was published. So we actually published the paper. We didn't die during the process, but then there's something called IEEE Micro Top Picks, which is the year after you publish the paper, you send it to a IEEE Micro magazine, and they select the top in quotation marks papers in the field to showcase to the community. And we got rejected from there. Let's take a look at the rejection reasons and how scientific they are. So this reviewer says, I poked around a bit, very scientifically. I should poke around. Are you poking around when you actually do these experiments? Okay, whatever that means. And DRAM vendors have already solved this problem. DRAM RowHammering appears to be a known problem. Okay. This other reviewer says it's going to have a minor impact, weak rejects, interesting paper for those interested in DRAM issues. It's very sloppy review. I wonder if it's possible to gain an insight into why this happens. We actually discussed that in the paper briefly. I seem to remember that during the presentation, because it was pointed out that DRAM manufacturers have already fixed the problem. Now, so where is the novelty and long-term impact? It's pretty aggressive, huh? And we know the story of RowHammer, right? How it's fixed. Okay, this is also interesting. Okay, I'm not going to read the whole thing because I want some cutting-edge research also. The mitigation solution offered is simple and effective. I like it, but I was not convinced that this paper will be cited in the future as one that opened up a brand new area of research and consequent use in practice. Okay, I don't know how to rebut this except for showing this picture and many, many other works that have had impact. You know, I don't believe in citations necessarily, but if you get more than maybe 500 citations, then paper had some impact, right? And in our area, actually, you don't get like tens of thousands of citations like in machine learning because everybody does tweaking of machine learning these days. Okay, anyway, so basically some things you cannot rebut. Okay, I already said this. Basically, we need to fix the reviewer accountability problem and the closed-mindedness problem. This problem is getting much worse, actually. And also, the system is getting overloaded because there are a lot of people actually who are doing research. And unfortunately, if their reviews are like this, the papers keep getting improved and submitted, resubmitted, resubmitted. So you're in this vicious cycle. Okay, just like main memory needs intelligent controllers, I think research community needs accountable and open-minded reviewers. So these are two fundamental problems, basically. You have a processor-centric system, we should be memory-centric. We have unaccountable reviewers, we should be accountable. Okay, so I actually gave a keynote talk at Micro a couple of weeks ago, and this was, if you don't want to go to the point of accountability, because it's a very revolutionary idea for some people, why have accountability, right? I can write these comments nicely and get away with it. Okay, at least you can patch the system a little bit, even though patching the system is not good in my opinion. You can accept papers liked a lot by some reviewers. If a reviewer gives a 5 and everybody else gives a 1, and if that review, if the rejection reasons are not really the paper is wrong, maybe that paper should get in, right? There should not be a majority voting because majority agreement among the reviewers kind of normalizes research that's by definition not so revolutionary or not so, let's say, controversial, right? So there's a lot of increasing negativity and bias, and we should also reduce negativity in the system, right? So in some conferences, for example, there's usually a champion of the idea, and more recent conferences, people have introduced anti-champion. Can we actually anti-champion some papers? Meaning reject as much as possible. Yeah, we already have enough negativity in the system. Basically, our litmus test should be to advance science efficiently, not how many papers should be accepted and whether or not everyone agrees with acceptance, right? I think science doesn't grow with consensus. It really grows with out-of-the-box thinking in the end. And if you're really interested in this sort of thing, you should really look at The Structure of Scientific Revolutions by Thomas Kuhn. Everybody who had a different idea was not able to get their idea easily accepted because there was a huge tension between the new system. For example, people have tried to show that the Earth revolves around the sun, right? This was not the general thinking. Now you're in 2025. Hopefully, most people believe that based on scientific evidence, Earth revolves around the sun. That was not the case until Newton, actually, right? Newton actually solidified it, and then after that, there was no question. But this took 200 years, 200 plus years to solidify, right? So Copernicus was the first one who did this, Brahe, and then after that, Galileo, and then, yeah, so these big minds, actually, they were not able to change that big mindset, right? So you see that science actually is not growing efficiently. So I definitely recommend that book, The Structure of Scientific Revolutions. And I think the solution is actually, if some people actually agree on acceptance, they should actually push through the work, and you should not require a consensus or majority voting, right? If there are 5 reviewers, if one of them is really excited about this and there's nothing wrong with the paper, it should be accepted. How does that sound? Right? Sounds really good. Okay, yeah. So basically, our litmus test should be to efficiently advance scientific endeavor. And people should ask, is my review scientific? Does it rely on a crystal ball? Is it correct? Okay, as students and producers of science, we can also do better. Basically, you follow your passion and you accept that there are people like this. There will be naysayers, there will be toxic comments, and you move on and you get the best out of the reviewers as much as possible. And also put it on archive so that you can get, once your work is ready, you put it actually, today there are places like archive where you can disseminate things. Okay, you should be resilient, no question about that. And focus on learning and scholarship is the most important thing, in my opinion, because some of these reviews are not focusing on learning and scholarship. And in the end, I strongly believe that the quality of your work defines your impact. And to enable that, you really need to work hard, no question about that. You can see that you don't only do the hard work to actually get the results and show something new, but you also need to do the hard work to convince sometimes unreasonable people that your work is good. Okay, but still, I think it's possible you can make a good or even great impact on the world, and you should not be derailed, in my opinion. And that's why we're having this discussion over here. And I think Richard Hamming thinks similarly. So yeah, I've read this paper, some of you, but I would recommend thinking about it this way also. Now let me go over a couple of reviews of Ambit also. Remember Ambit? Okay, this is something interesting. So this paper was rejected 4 times before it got accepted. And we thank all of the reviewers because they have very valuable comments. Some of them do, not all of them. So this is clearly the first work on charge sharing based bitwise operations in DRAM. It extends and completes our IEEE Computer Architecture Letters 2015 paper. It's disruptive. It spans algorithms to circuits, requires hardware-software cooperation for adoption. You know that already. But it did lead to a lot of work in DRAM and NVM. The work continues to build, and it was rejected from 4 conferences. Let's take a look at the rejection reasons. By the way, it was not always called Ambit. It was called PuDHammer before we, I guess, when we started the research. And you can see it was rejected from ISCA, Micro. And you can see the review over here. Again, there are some reviews that are actually pretty positive, 5.5. And then there's 2.2, 3.4, and it gets rejected. I believe this should be accepted basically based on my criteria, right? These people actually like the work, so they should get it accepted. But of course, there are some self-proclaimed expert reviewers that give it a 2 over my dead body. But I'm not going to say that it's over my dead body type of review. Okay, it's good to think about that. HPCA, this is rejected. There's definitely an over my dead body review. And the rest is actually relatively positive. The color actually is positive, as you can see, right? This was actually the worst rejection, basically, for this paper. I'm going to go over that review. ISCA, again, you have another over my dead body reviewer, but there's always positive people also, right? So this paper didn't change a whole lot during those iterations. Maybe something's added, something's writing got better, etc. So let's take a look at some of the reasons. This is ISCA 2016, one of the first submissions. Very clever, novel idea. That's what we should encourage. Great potential speed up and efficiency gains. Sounds good. Combined, accept, right? Probably won't ever be built. Weaknesses. Not practical to assume DRAM manufacturers will change DRAM in this way. Okay, is this a scientific review? Yeah, how can I actually rebut this, right? Does this review have a crystal ball, right? And they basically have charted out the entire space of the universe or multiverses, and they figured out that this will never be built and reject. This is a reject. I don't remember if it's a weak reject or reject, but it's not. Basically, the paper didn't get accepted. Okay, and actually, very interesting and novel. Okay, let's see if there's anything I want to say over here. Blah, blah, okay. It's hard to believe that the commodity DRAM industry will incorporate this into their DRAM standard process. Blah, 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 blah. Another review. This requires significant modification to DRAM that will only help this type of bitwise operation. It seems unlikely that something like this will be adopted. Again, you can see, right? First of all, it's not a bad operation, bitwise operation. It's actually functionally complete in Ambit, even though it's not built. It's possible to do anything in the substrate, as you know, right? Okay, I'm not really convinced. Again, the manufacturer would really consider. I'm going to go through this quickly because, okay, this is also interesting. I do not find architectural innovation, even though the circuits technique benefits architecturally by mitigating memory bandwidth and blah, blah. This paper suits better. Now, you're another reviewer who's an architect, and he says, or she says, this paper suits better to be peer-reviewed and published in a circuit conference or with a fabricated chip in ISSCC. They want us to fabricate a DRAM chip to demonstrate this. Nobody is capable of this except for the manufacturers who are not going to do this kind of research. But they're very interested in this kind of research because Ambit started the type of research that culminated more recently with Ismail's FCDRAM work, for example, and they're very interested in potentially building this sort of thing right now. Okay, this is actually the most interesting one. This is, you can see that this person is a strong reject. They have passing familiarity with this area, although their comments actually are very confident for passing familiarity. The person says, I'm skeptical this would benefit real-world computations. I've never seen real-world program profiles with hot functions or instructions that are bitwise operations. The fact that you have never seen it doesn't mean that they don't exist, first of all. And maybe there's a paper called Hacker's Delight. I would recommend people to look at it. It's a beautiful paper. There's a lot of, it's all about bitwise operations, basically. Hacker's Delight. If you're interested in looking at bitwise things, that's a great paper. And actually, we referenced that paper, I think, in the Ambit paper. And also, clearly, we have seen bitwise operations. People have built actually databases, right? Okay, the second one is even more interesting. On the other hand, I have seen system profiles that show non-trivial time zeroing pages. I suggest retooling your work to support page zeroing and evaluating that with a full system simulation. Take a look at why the Linux kernel zeros pages. You might be surprised at the possible impact. Go write a different paper, which is already written. Row clone. It sounds interesting, right? Okay, yeah. What do you say to this reviewer, right? That's why you should be resilient and you should ignore some things. Okay, I mean, I'm not going to bore you more, but you can read these. You can see this is another strong reject. And I don't want to go through this because we have other things to cover as well. Another review from ISCA. This is weak reject. And in the end, nitpicks. The reviewers were uniformly positive about blah, blah, but we reject you. Okay, we acknowledge all of the reviewers, basically. Okay, and finally, it was accepted to micro because we satisfied the majority. That's the goal, you know. And the majority is positive, and this not positive guy apparently was not an over my dead body positive, or maybe he got killed after he wrote this review. That we were lucky in the end, you know. You see, this is actually not a joke, you know. So there's someone who said that science advances over dead bodies because people who have very set things die eventually and get out of the universities. So young people can advance new things and can thrive after that. I think these older people should be open-minded so that younger people can thrive even though older people don't die, right? Okay, so that was a joke, but actually someone said this. Okay, so another lesson, make sure you write your paper such that you have a majority. Actually, these days, it's not even a majority. It's a +2 majority. If you have 6 reviewers, you should convince 4 of them. Okay, anyway. Well, some questions to ponder, and then I'm going to leave the stage for these guys. But basically, do all research ideas need to be commercially viable? I don't think so. If yes, when? Immediately? How can you predict the future, basically? This basically destroys, I think, the reviews that say the manufacturers will not implement. Can a non-viable idea become viable? Right? Should we give it a chance? Or even if it's not going to become viable at any point in time, can it inspire something that could be useful? Right? That's the open mind right now, right? Instead of saying DRAM manufacturers won't implement it, see what it could enable. Right? Does a paper have to solve all problems with an idea? I don't believe so. Or can it do just enough to enable fast and efficient progress? Right? Radar, for example, clearly didn't solve problems, but enabled a lot of work on retention time issues. And this is another difficult question. Are all reviews bias-free? Definitely not. Are they hidden or visible conflict of interest free? That's also definitely not. People have a lot of conflict of interest, actually, when they make these decisions. How do you overcome this problem? More accountability, basically, and more transparency. And also more acceptance. We can accept more works and enable fast progress. And maybe some of them will not be completely perfect, yes, but at least will not be overwhelmed. Okay, basically, I don't think we lose from being more constructive. Okay, in the end, our litmus test should be to efficiently advance scientific endeavor. And if the reviewer doesn't satisfy that litmus test, it should be discarded. If a paper doesn't satisfy that test, that also should be discarded. I agree. But I think there are many ways to advance scientific endeavor if you're open-minded. Okay, I'll acknowledge some people for these talks, but you're going to hear some talks. So a lot of the works that we have presented in memory robustness were done by people, you see, and some of them are going to describe their research. If you want to learn more about them, you can read the newsletters that we have. Okay. And actually, this research was supported by a lot of these companies as well. So definitely industry is interested. But why are the papers getting rejected? I don't know. There's a system that's built that's very bureaucratic. Okay. And we do open source a lot. And if people are interested in doing research in these areas, actually these tools are used by companies as well as universities. So you are actually at a point where you can do a lot of research and you can work with the internal versions of these tools that are better than what we uploaded over there. And Emulator 2 is one example of this. If you're interested in working on memory, NISA, where there's a big maintainer of this tool. Hao Song is right now on an internship in the US, so he's not here, but when he comes back, he's also a good person. And DRAM Bender, you know, also, and people like Ismail here worked a lot on DRAM Bender, but ABACuS is also on an internship in the US, so when he comes back, he's also a good person. Hao Song also. Yeah, by the way, this was rejected twice also. And then we decided to send it to TCAT, a journal essentially. And this already has had a lot of impact. People have actually been using DRAM Bender. It's not an easy infrastructure to use. It's much easier than SoftMC, no question about that. But it's enabled a lot of work in different parts of the world, right? We were discussing Korea, where Japan, US. Who's doing it in Europe other than us? He's not Europe. He's in the US. Yeah. Okay. Anyway. Okay. Anyway. Okay. There's also actually, if you want to go a little bit deeper, there's an older version of the RowHammer and DRAM exploration course and some emerging memory systems course. We actually have some Emulator DRAM Bender tutorials that are out there. But if you want to do work in this area, definitely talk with people. And if you're online watching, you can actually make use of these resources online or contact us. We're happy to help anyone who's doing work in this area. Okay. Any questions? Okay, let's take a break. And then we're going to hopefully finish all 5 papers. Some of them may be shorter, but let's take a break until 2:45. And then we're going to continue with the papers. Am I audible? Hello? Hello? Exactly. Okay. Thanks a lot for the introduction. Hello, everyone. I'm Ismail. Today, I'll discuss the latest papers, as Onur said, ColumnDisturb and PuDHammer. And that's a brief self-introduction, what I already introduced. So my research interests are processing in memory, computer architecture, specifically processing using DRAM. And lately, I've been working on DRAM safety, security, and reliability, DRAM robustness. I'm broadly interested on many things, like hardware security, etc. And this is today's agenda for my part. It's the first one I'll talk about is ColumnDisturb, published in Micro 2025. I presented in 2 weeks ago, I think, or 3. And the other one is PuDHammer. It's also published in this year, ISCA 2025. And let's start with the first one, ColumnDisturb. And its full title is ColumnDisturb, Understanding Column-Based Disturbance in Real DRAM Chips and Implications for Future Systems. So this is a typical DRAM-based computing system with a CPU and a DRAM module, as you know, and DRAM module has many DRAM chips. So within each DRAM chip, we have many DRAM banks. So within each banks, we have multiple subarrays, and each subarray consists of 2-dimensional array of DRAM cells. A row of DRAM cells called DRAM row, and they are connected through word line. And thousands of DRAM cells are connected to sense amplifiers via bit lines. So as you know already, but let me refresh your mind, DRAM suffers from read disturbance, and read disturbance breaks memory isolation. A prominent example is RowHammer. Here I'm going to use a different sketch. It consists of 3 subarrays, and each subarray is separated by the sense amplifiers, and each subarray consists of, again, many DRAM rows. And here, what we do in RowHammer is that we have aggressor row, we keep repeatedly hammering that aggressor row. And we induce bit flips in nearby, immediate neighboring rows, which we call victim rows here. And the other read disturbance phenomenon called is row press. Instead of hammering, we keep open the aggressor row for a longer time. And again, we have bit flips in nearby rows. So to sum up things, RowHammer and row press are read disturbance phenomena, row-based read disturbance phenomena that affect only a few neighboring rows. And most of the mitigations work by either detecting high row activation count or high row time, depending on your attack, and refreshing a few neighboring rows. And as you already seen that detecting and refreshing even only a few neighboring rows is shown to be a difficult problem. People are still developing solutions, even copying the solutions of some mitigations. So in this study, we ask this research question: what if there is a much worse read disturbance phenomenon that affects thousands of DRAM rows through bit lines? So turns out there is one, which we call ColumnDisturb. We show that by repeatedly opening or keeping DRAM row open, it is possible to disturb many DRAM cells on the same DRAM column. So here is the same set of sketch, and with ColumnDisturb, the activation of a single row concurrently affects DRAM cells across as many as 3 DRAM subarrays. It translates to up to 3,072 DRAM rows. And let's see how ColumnDisturb works. So ColumnDisturb is a column-based read disturbance phenomenon that affects thousands of rows. So whenever we activate a row, what happens is that an activation of a row perturbs all the columns that connected to that row. So as much as 64,000 columns. And those columns spans across subarrays. So as a result of this, cells in all perturbed columns are disturbed when you do the activation of a single row. So as a result,
all columns in the aggressor subarray, and also half of the columns in the neighboring subarrays are affected. Why the half of the columns in neighboring subarrays are affected? It is because open bitline architecture. Columns of a single row span multiple subarrays. As a result, those columns in the top and the bottom subarrays are also affected. So we call them as a victim column. And ColumnDisturb is fundamentally different. It affects cells that are vertically connected to same bit line. Here in RowHammer and RowPress, the DRAM rows were the victims. Now in ColumnDisturb, DRAM columns are the victims. So, and as you can see, ColumnDisturb affects cells across both the same subarray and multiple neighboring subarrays. And it translates to, as we discussed, 3,072 rows total. So how do we test this phenomena? By using our infrastructure, as you already familiar with, DRAM Bender. It enables us to have fine-grained control over DRAM commands, temperature, and timings. And this is another version of DRAM Bender, which is for HBM2 DRAM chips. And again, our laboratory to test many DRAM chips and HBM chips in parallel. In this study, we specifically test 216 DDR4 chips and 4 HBM2 chips from 3 major manufacturers, SK Hynix, Micron, and Samsung. And we cover different die revisions and chip densities, essentially could be different DRAM architectures. So what we do to, let's say, to test, our first methodology is to prevent the source of interference during the core test loop. So we avoid refreshing victim rows and no read disturbance mechanisms and no error correcting codes to observe all bit flips. And we also filter out retention and RowHammer and RowPress bit flips to only observe, to demonstrate that ColumnDisturb bit flips are new and unique. And there are a lot more things that we do to, let's say, prevent the source of interference, and you can take a look at the paper for those. And we use 3 key metrics in this study to assess the vulnerability. The first one is minimum time required to induce the first ColumnDisturb bit flip. You can think of this as HC first, but it translates to the time. And here lower is worse. And the second one is number of ColumnDisturb bit flips in a subarray, and here higher is worse. And lastly, number of rows with ColumnDisturb bit flips in a subarray, and here is higher is worse. Basically, the last one shows the effect, how many rows are affected in a subarray. So in this experiment, we have one aggressor row, and as a result of ColumnDisturb, we have 3,072 victim rows, 3,071. One of them is aggressor. So we use a similar access pattern as the prior works, where we keep repeatedly hammer or press one aggressor row, and we record the bit flips in victim rows across 3 subarrays. So, and we test many different parameters. We carefully sweep data pattern, temperature, aggressor row on time, and DRAM refresh interval, and aggressor row location. And we test up to 49,000 DRAM subarrays, which translates to more than 4.5 million rows. So this takes, for us, this takes more than 1.5 years to do this study, because you need to cover a lot of bit flips and a lot of rows, as the bit flips can happen across 3 subarrays, not just +1 or -1 as we saw in RowHammer and RowPress. So let's see the results. So we have 5 key takeaways, major ones, and the first one is ColumnDisturb is a widespread read disturbance phenomenon, and it becomes worse as DRAM technology scales down to smaller node sizes, similar to what happened in RowHammer and RowPress. So let's see the first result. In the y-axis, we have the time to induce first bit flip in a subarray in terms of milliseconds. And we have 3 manufacturers, SK Hynix, Micron, and Samsung. And each X label shows the DRAM chip density and die division. And as you can see, all the tested 216 DDR4 chips are vulnerable to ColumnDisturb. And for the second observation, let's focus on the first manufacturer here, SK Hynix. And as you can see, from 8 gigabit A die to 8 gigabit D die, minimum time to induce the first bit flip reduced by 5.1 times. So note that D die is newer die generation than A die. So it's in alphabetic order. You can think of that. And it's the same for 16 gigabit chips. From 16 gigabit A die to 16 gigabit C die, which is newer one than A die, it reduces by 1.3 times. And we conclude that newer chips tend to be more vulnerable to ColumnDisturb, similar to RowHammer and RowPress. And this observation is consistent across all tested manufacturers. In Micron, for example, we see 3 times reduction, and in Samsung, we see 2.5 times reduction. And for the third one, we focus on the minimum that we observe from across all tested chips. And as you can see here, for Micron's 16 gigabit F die, we observe a bit flip in 64 milliseconds, which is very close to 64, 63.6. And we conclude that some real DRAM chips experience ColumnDisturb bit flips within nominal refresh window under nominal operating conditions. And this, now moving on to second key takeaway, which ColumnDisturb induces bit flips in thousands of DRAM rows and is different from RowHammer, RowPress, and retention failures. So let's take a look at the results. Now here in the y-axis, we have number of bit flips, and the x-axis, we have the row addresses covering the first 3 consecutive subarrays from row 0 to row 3072. And each 1024 rows belongs to one subarray. So subarray row 0 to row 1023 belongs to subarray 0, and row 1024 to row 2047 belongs to second subarray, and so on. And in this RowHammer, RowPress, and ColumnDisturb experiment, we use one single aggressor row, which is located in the middle row of the aggressor subarray. It's, I guess, 1536 row. So here, let's take a look at the first RowHammer and RowPress results. As you can see here, there are only 2 dots for RowHammer and RowPress. It's exactly the +1 and -1 of the aggressor rows. They are inducing a lot bit flip, as you can see, like 7,500 and more than 5,500. But it's only in +1 and -1. And this experiment is done for 16 seconds. So we keep repeatedly hammering for 16 seconds. And we conclude that RowHammer and RowPress induces bit flips only in the immediate neighboring rows of the aggressor row. And now let's take a look at the retention. As you can see, retention, regardless of the row address, it's almost constant. It's around 500 for every row because it's retention, right? It's happening randomly. And for the last one, it's the ColumnDisturb. So as you can see, ColumnDisturb spans across 3 subarrays, affecting all rows, and induces bit flips much more than retention, and affects many more rows than RowHammer and RowPress. In RowHammer and RowPress, you have only 2 rows. But here you have 3,071 rows affected by ColumnDisturb. And it is at least 4 times more bit flips than retention. So, and the third key takeaway is showing the bit flip characteristics. The bit flip directionalities of ColumnDisturb and RowHammer and RowPress are significantly different. So in the y-axis, you see the number of bit flips in a subarray. You can think of number of bit flips directly. So here we have 2 subplots, and x-axis shows the refresh interval. So you can think of refresh interval as DRAM refreshes all rows within the refresh interval. So 1 second means DRAM refreshes all rows within 1 second. So you can think of that normally it was 64 milliseconds. Now we extend it to 1 second. And bit flip direction 1 to 0 means cells initially has 1 and experience bit flip and thus becomes 0 after the experiment. And bit flip direction 0 to 1 means the vice versa. Cell initialize with 0 and experience bit flips and thus become 1. And here are the results. And as you can see, ColumnDisturb induces bit flips only 1 to 0. There is no bit flip there's no bit flip from 0 to 1, which is the same as retention. But this is very different from RowHammer and RowPress. As you might seen from the previous lectures, RowHammer and RowPress induces bit flips on both directions. And this indicates underlying phenomenon is very different than RowHammer and RowPress. And the fourth key takeaway is significantly more rows are vulnerable to ColumnDisturb than retention failures. So here in the y-axis, we see number of rows with bit flips in a subarray at 65 degrees Celsius. And in the x-axis, we see refresh interval. So 64 means the nominal one. And as we go right, refresh interval increases up to 1 second here. So let's take a look at the first micron. So each color indicates a different underlying mechanism. One of them is ColumnDisturb, the other one is retention failures. So as you can see, for 1 second, ColumnDisturb affects 30 times more rows than retention. So you have, I don't know, 20 rows that experience retention failures. But now here, for the ColumnDisturb, there are more than 300 rows that experience ColumnDisturb bit flips, which is again very different than, as you can see, from retention. And we conclude that ColumnDisturb induces bit flips in significantly more DRAM rows than retention failures. And this is also consistent across other manufacturers. Even in Samsung, it's much more larger than Micron. So this trend is consistent across all tested manufacturers. So for the last one, which is also different than RowHammer, as temperature increases, DRAM chips become more vulnerable to ColumnDisturb. As you may remember from deeper look paper, so in the RowHammer, there was bounded temperature range. Not when you increase the temperature, it's not always increasing the HC number of bit flips. But here, it's different. So let's see the results first. In the y-axis, you see time to induce the first bit flip in a subarray. And in the x-axis, you see the temperatures from 45 to 95 degrees Celsius for each manufacturer. And these red labels in the y-axis shows the minimum that we observe, which is from 95 degrees Celsius. So first, let's take a look at SK Hynix. So from 45 degrees Celsius to 95 degrees Celsius, the time to induce the first bit flip reduces by 9 times. And we conclude that it's significant. Time to induce the first ColumnDisturb bit flip significantly reduces as temperature increases. And this trend is consistent across all tested manufacturers. And for example, for Micron, it's more than 5 times. And for Samsung, it's 2 times. And as you see, the observations that I showed you could have very significant implications for as well as future systems and retention failures. So we take a look at major implications. Where the first one is implications on future computing systems. Why? Because ColumnDisturb could jeopardize the robustness of computing systems. Because first, ColumnDisturb bit flips occur very far away rows from the aggressor rows, even in the nominal operating conditions. And second, it's getting worse. Newer chips are more vulnerable. And the second line of implications is on retention-aware refresh mechanisms. So ColumnDisturb dramatically decreases the benefits of these mechanisms. Because first, at long refresh intervals, as you see, so that there's a 30 times difference between retention and ColumnDisturb bit flips, right? So a large majority of rows experience ColumnDisturb bit flips. And ColumnDisturb induces significantly more bit flips than retention failures. So for the first line of implications, so ColumnDisturb bit flips occur in very far away rows from the aggressor row. For example, one of the bit flips that we observe in the nominal refresh window is actually 374 rows away from the aggressor row. So why this is important? Because most of the disturbance mitigations refresh only a few neighboring rows, usually +1 and -1. But if you account for like half double kind of blast radius, +2, -2. But here it's 374 rows away. And even refreshing only few rows is shown to be a difficult problem that Nisa will discuss later. And to, let's say, mitigate these bit flips, we describe and analytically evaluate 2 solutions. First, you can increase the DRAM refresh rate to mitigate these bit flips from happening, right? But it reduces the DRAM throughput by 42%. And the second one is proactively refreshing victim rows that you will have, before bit flips happening, you start refreshing the rows one by one. And to mitigate, it's kind of similar to increasing the DRAM refresh rate, but for the just rows that could be affected. For example, if you have one aggressor, now you have 3,000 rows, right? You don't need to increase the refresh rate for the other rows. You can just increase the refresh rate for the rows that could be affected, basically that 3,000 rows. But this turns out to be still reducing DRAM throughput by more than 12%. So we conclude that we still need intelligent solutions to also low overhead solutions to mitigate ColumnDisturb bit flips from happening in the future chips. And you can find more details about the implications in the paper here. And the second one is the implications of retention-aware refresh mechanisms. So these mechanisms leverage the heterogeneity in DRAM cells data retention time. So here is the DRAM bag consists of, for example, 6 rows. So most of the rows do not need to be frequently refreshed, as shown by prior work like Radar, Avatar, and so on. So there are, for example, here 2 rows, retention weak rows, that needs to be frequently refreshed, but other rows doesn't need to be frequently refreshed. So those are less frequently refreshed. You can increase the refresh interval for those rows. However, in the presence of ColumnDisturb, now less frequently refreshed rows become vulnerable to ColumnDisturb because ColumnDisturb induces bit flips in much more rows than retention failures. So as a result, these mechanisms won't work in the presence of ColumnDisturb. So you need to mitigate ColumnDisturb for these mechanisms to work. But as a result, the benefits of retention-aware refresh mechanisms is significantly reduced in the presence of ColumnDisturb because normally you had just, for example, 2 rows to frequently refresh, right? But here now we have 3 more additional rows. It's like having the normal refresh rate almost, right? So in the paper we have analysis, the evaluation, how this could affect it, and we observe that actually you will reduce the performance benefits by 50% almost. So there are a lot more things in the paper, many more characterization results, like the average voltage level on the per third columns, which is kind of interesting to me, and temperature, spatial variation, access pattern, data pattern, aggressor one time. I mean, in the paper you will find more than 20 figures with the results. And there are detailed analysis and details and analysis on the implications that I just give you a brief introduction. And we also evaluate the effectiveness of ECC. And turns out that ECC is not effective as you would guess. And there are more details on the mitigation mechanisms and implications on the retention-aware refresh mechanisms. So for this one, we take an example of Radar and see how Radar works in the presence of ColumnDisturb, and so on. So the paper is available in arXiv. We are still working on it to extend, and there are a lot more to do, and we'll add much more content in the paper. And let me conclude for this part of my talk. So we demonstrate and extensively study a new widespread disturbance phenomenon in real DRAM chips, ColumnDisturb. So to refresh your mind, ColumnDisturb is fundamentally different than RowHammer and RowPress. They're row-based disturbance phenomena that affect only a few neighboring rows. But here, ColumnDisturb is a column-based disturbance phenomenon affecting more than 3,000 rows. And we characterize a bunch of DDR4 and HBM2 chips. And it affects, we observe that ColumnDisturb affects all cells, and it's getting worse as DRAM technology node site reduces. And it's different from RowHammer, RowPress, and retention failures. And we describe and evaluate 2 major implications of ColumnDisturb. One is on the robustness of future systems, and we observe that we need more intelligent and low overhead solutions. And the second one is ColumnDisturb makes retention-aware refresh mechanisms much less effective. And we conclude that we hope this work inspires system-level, architectural level, and device-level solutions and understanding to enable ColumnDisturb resilient future systems. So that concludes this part of my talk. I can get questions if you have any. Yes. Toggling? Throttling. I see. It's like BlockHammer. So that could be one thing, but the issue is that you cannot use BlockHammer as it is. Why? Because now you have 3,000 rows, right? So for throttling, what you do is you blacklist the ones that you repeatedly activate one row. But here you can traverse 3,000 rows, and you will only have 72 victim rows. Instead of giving, so in RowHammer and RowPress, you need to frequently access 2 rows, for example, for double-sided write. But here you can just access 3,000 rows. And then, so your mechanisms now for throttling needs to be more intelligent to somehow capture that it's traversing the same set of rows in those subarrays, and those could induce bit flips. But even a benign workload could do that, right? For example, streaming. You will stream from 3,000 rows, and 72 rows will be the victims over there. So we really, I think that could be one potential solution, but I think it needs to be revisited in the presence of ColumnDisturb. Good question, thanks. Yeah. Let me try to find that slide. I'm sorry, a lot of slides. Yeah, this one, you mean. So why Samsung has lower? So first of all, I don't know. But probably the thing is that in Samsung, we test the newest chips. So in SK Hynix, I think we test older chips, like from 2016 or 17, but Samsung ones, as far as I remember, they're pretty new ones, like all of them are 16 gigabit. That's why, so as we discussed in the first takeaway, right, like it's getting worse. So here it's already worse, as you can see in the Samsung. So it's really still getting really worse, but not as SK Hynix. Probably these are from like 2016 and 17 chips that are not, let's say, vulnerable as the newer ones. And that's why when you decrease the temperature, you get like, now it's more than a second, as you can see. Yeah, exactly. So the range is smaller. And I think it's because of the generation of the chip, basically. Yeah, but good catch. Yeah. Any more questions? Okay, if not, I'll move on to the second part of my talk. Okay. So this one is PuDHammer. So this paper is, again, published in ISCA 2025 this year, and it's called Experimental Analysis of Read Disturbance Effects of Processing using DRAM in Real DRAM Chips. So we will see how in DRAM operations, processing using DRAM operations actually cause read disturbance, and it significantly makes things much worse. So here's the executive summary. As you might know, processing using DRAM is a promising paradigm to elevate data moment bottlenecks between main memory and processing units. So DRAM can perform many processing using DRAM operations by activating multiple DRAM rows in quick succession or simultaneously, which we broadly refer as multiple row activation. And modern DRAM is subject to read disturbance, even repeatedly activating a single DRAM row induces bit flips in unaccessed rows. But here, think about that. We have multiple rows activated simultaneously or quick succession. In contrast to RowHammer and RowPress, that you repeatedly activate a single row at a time. So problem is no prior work studies the read disturbance effects of this multiple row activation. And our goal is to understand and analyze the read disturbance effects of multiple row activation. And we test 316 DDR4 chips from 4 major manufacturers to study this read disturbance effects of multiple row activation, which shortly we call PuDHammer. We observed that PuDHammer significantly exacerbates DRAM read disturbance, so causing up to more than 158 times reduction in the minimum hammer count in this first bit flip, basically HC first. And we observed that PuDHammer bypasses in DRAM RowHammer mitigation DDR4, which is broadly referred to as target row refresh TRR, and induces more than 10,000 times more bit flips than RowHammer. And we try to adapt per row activation counting called PRAC for PuDHammer, and we observed that adapted solution incurs an average system performance overhead of more than 48%. So here's the outline of my talk, and I'll quickly go over the background. So processing using DRAM, as you might know, it uses analog operational principles of DRAM cells that perform computation. And multiple row activation is a key technique to realize many in DRAM and or kind of operations. And we categorize multiple row activations into two. First is consecutive multiple row activation, COMRA, and second is simultaneous multiple row activation, we call SIMRA. So consecutive multiple row activation, COMRA, is used for row clone. Basically, for real DRAM chips, what you do is that you violate the timing of pre-charge command greatly, and you activate two rows consecutively, which you then use to copy a source row to destination row. And for simultaneous multiple row activation, in real DRAM chips, what we do is that we activate two rows in quick succession to simultaneously activate multiple rows. Instead of having 36 nanoseconds of TRAS between activate to pre-charge, now we have 3 nanoseconds. From pre-charge to activate, instead of having 14 nanoseconds, now we have 3 nanoseconds, which then confuse DRAM and activates many more rows. So, and as you already know, even activating a single DRAM row disturbs the data integrity of other unaccessed rows. And one example is RowHammer. And our goal, our first problem is in this work we tackle is that no prior work investigates the read disturbance effects of multiple row activation. And our goal is to understand how multiple row activation affects the read disturbance vulnerability in DRAM chips. So again, we use this same testing infrastructure DRAM vendor to have the fine-grained control over commands, timings, temperature, and voltage. And we test 316 DDR4 chips from 4 major manufacturers. Usually you see SK Hynix, Micron, and Samsung, but here we also test Nanya chips. And we cover different die revisions and chip densities. And let's see the first effect, read disturbance effect of COMRA, which is row clone. So as I recall, it's the command sequence is this: activate source, you wait for nominal timing parameters, you issue per charge, you violate that timing around 7.5 nanoseconds or 9 nanoseconds, depending on your real DRAM chip, and then you issue and activate to destination, which will enable you to copy source to destination. So here's how we do hammering, and there could be two scenarios that are two major scenarios. One is double-sided, where you sandwich a row. Here, how we enable that in COMRA is that we copy one source to destination rows while sandwiching a victim row. And for the single-sided, so now we have actual two rows, right? So how do we do single-side attack? Basically, we are copying source row to destination row that are pretty far away from each other, like 100 rows, 200 rows far away from each other. That makes things single-sided, but hammering at the same time. So we carefully sweep row addresses to cover many DRAM rows and timing parameters between pre-charge to activate to understand the phenomenon better. And we also test many data patterns and temperature levels. And we use a metric called HC first, as you might already know, is minimum hammer count required to induce the first bit, lower is first here. And it's one scenario of double-sided where we perform COMRA repeatedly, and between each copy operation, we obey the timing parameters, basically in between activation destination to activation source. So let's look at the first result. In the x-axis, you see the manufacturers, and the y-axis, you see the lowest HC first observed from that manufacturer across all tested DRAM chips. So, and each color will indicate either RowHammer or COMRA. So here let's look at the SK Hynix, and as you can see, its double-sided COMRA decreases the lowest HC first by almost 14 times compared to double-sided RowHammer. For RowHammer, it was previously more than 6,000. Now it's 447. And it's also consistent across all tested manufacturers. And now let's take a look at all the victim rows that we test. Here in the x-axis, y-axis, you see the HC first change. And in the x-axis, you see the DRAM rows sorted by reducing HC first changes. And I'll go through the plot with you now. So P1 to P100 represent 99 of tested victim rows. And similar to P50 to P100 represents 50% of tested victim rows. And negative HC first change means CoMeT reduces HC first. For example, HC first change of minus 50 means HC first reduction of 50%. As an example, RowHammer HC first was 100. Now CoMeT's HC first is 50. So we observe that more than 99% of tested victim rows experience lower HC first. And we conclude that double-sided CoMeT decreases HC first for a large fraction of rows compared to double-sided RowHammer. And key takeaway from these experiments are CoMeT exacerbates DRAM's vulnerability to read disturbance in all 4 major manufacturers. And now let's take a look at read disturbance effect of CYMRA, which is more interesting actually. So recall that what CYMRA does is that it violates timings between each latency in this CoMeT sequence and activates multiple rows simultaneously. So here, again, we carefully sweep row addresses, timing parameters, data pattern, and temperature. And let's take a look at double-sided CYMRA versus RowHammer in terms of lowest HC first. In the x-axis, you see number of simultaneously activated rows. 1 represents RowHammer because we just activate 1 row at a time in RowHammer. And 2, 4, 8, and 16 is the different versions of CYMRA, where you activate 2, 4, 8, and 16 rows. And lowest HC first, again, minimum hammer count in this first bit flip, observed in all tested DRAM chips. As you can see, what we observed that RowHammer lowest HC first is 4123. But it goes from there to 26, which is 159 times lower. So we observe that double-sided CYMRA decreases lowest HC first by 159 times compared to double-sided RowHammer. So in order to induce a bit flip using simultaneous multiple row activation, you only need 26 CYMRA operation to just sandwich that row. And this trend consistent across all tested number of simultaneously activated rows. And now let's take a look at all victim rows. Here, what we first observe is that more than 99% of tested victim rows experience lower HC first, and more interestingly, at least 25% of tested victim rows experience more than 99% of HC first reduction. That means that if RowHammer HC first is 100, CYMRA's HC first is 1. So we conclude that double-sided CYMRA significantly decreases HC first for a majority of rows compared to double-sided RowHammer. And the key takeaway is this, very similar to CoMeT. CYMRA drastically exacerbates DRAM's vulnerability to read disturbance. And now let's take a look at how can we mitigate PuDHammer. First, we will analyze the effectiveness of existing in DRAM RowHammer mitigation against PuDHammer. And second, we will try to adapt RowHammer mitigations to account for PuDHammer bit flips. So let's take a look at the first one. So as you might know, but let me refresh your mind. So target row refresh means that DRAM vendors equip their DRAM chips with a proprietary mitigation mechanism known as target row refresh. So the key idea is that TRR refreshes nearby rows upon detecting an aggressor row. Here, you see that memory control with a TRR equipped DRAM chip. So upon assume that TRR detected row 2 as an aggressor. What it does is that it issues refresh, and whenever you issue TRR-induced refresh, it will refresh the neighboring rows of detected aggressor. In this scenario, it's row 1 and row 3 will be refreshed. So, and we test many access patterns. And here, the first one is RowHammer without TRR. In the x-axis, you see number of aggressors that is tested to induce bit flips. So we observe that RowHammer induces more than 10,000 bit flips without TRR. In the presence of TRR, now you still induce bit flips, but the effectiveness of RowHammer is reduced. Now you induce at most like 55, less than 60 bit flips with TRR. For COMRA, now it's very similar to RowHammer. Again, without TRR, you induce 10,000 bit flips. With TRR, it's more than RowHammer, but still the effectiveness is reduced. It induces 1.1 times more bit flips than RowHammer on average in the presence of TRR. But now with CIMRA, things are a bit different. So without TRR, you induce 240,000 bit flips. But with TRR, you still induce a lot bit flips, like 180,000 bit flips with TRR compared to 60 bit flips. So on average, CIMRA induces 11,340 times more bit flips than RowHammer. So this could be because of one thing, that TRR detects aggressor upon an activation, right? So it samples the activation. But internally with CIMRA, what you do is that you just issue 2 activation, but you can activate 1632 rows internally. So TRR is not aware of activating other rows. It's just aware of 2 rows. As you can see, 2 rows have very, like compared to others, less bit flips. But still 32, 4, 8, and 16 is still there. So, and then since we see that in TRR, it's not going to solve it, we try to adapt RowHammer mitigations to account for PuDHammer. And for this one, we choose PRAG, which is introduced by JEDEC in last year, April. So what it does is that, again, I think Nisan will cover it, but just a sentence to summarize it, now you have deterministic row activation counters in DRAM that deterministically counts the activation and then refreshes the victim rows. So a naive approach, what we do is that we reduce the RowHammer threshold to CIMRA's levels observed HC first. So normally you will configure your threshold with 4,000 with just RowHammer. Now, since we have CIMRA's hammering, now we have threshold is 20. And the other one is weighted counting. So we increase the counters based on the vulnerability caused by the operation. So RowHammer needs 4,000 activations, but CIMRA needs 20 activations, right? So what we do is that whenever you do activation, you increase the counter by 1. Whenever you do CIMRA operation, you increase the counter by 200, so that you will have heterogeneous counting. So the methodology is what we do. We use Remulator 2, and here's the system configuration, and we have 65 core multi-program workload mixes. What we have is that in this scenario, we have 4 cores that is normal like CPU, and we have 1 core that issues PUD requests to the same DRAM that is shared by this 5 cores. Let's take a look at the results. So x-axis shows the intensity of PUD operations. So from left to right, the intensity increases. So 125 means DRAM performs PUD operations in every 125 nanoseconds. Instead of serving other requests from normal processors, now it's serving processing using DRAM operations. So intensity is too much. But if you go to 16,000, which is 16 microseconds, in every 16 microseconds, DRAM performs PUD. It's not that intense compared to 125. And y-axis shows the normalized weighted speed up, normalized no RowHammer mitigation. And each color represents the technique. One of them is naive, the other one is weighted counting. As you can see, weighted counting greatly outperforms the naive until 2 microseconds. So basically, it's almost the middle point of the intensity scale here. But once you make things more intense, the PUD operations more intense, now they're almost the same. Because almost every 2 activation, one of the 2 activations is CIMRA operation. As a result, weighted counting incurs an average performance overhead of 48%, and the maximum is almost 99%. So again, in order to mitigate the PuDHammer, we need better solutions, hopefully a low-cost solutions that we don't face this in future. So there are, again, a lot more characterization results in the paper. And we also, interestingly, combine the RowHammer and with PuD. So basically what we do over there is that you do RowHammer normally, and then you do CyMR operations. So instead of doing 4,000 RowHammer operation, you first do 2,000 RowHammer operation, then do CoMRA or CyMR or vice versa. So basically we combine normal activations with CoMRA and CyMR. And we observe that the combined pattern is much more effective than RowHammer alone. It reduces HC first by more than 1.6 times on average. And we have details and analysis on mitigating PuDHammer. We actually discuss many directions, how can we modify DRAM chips to mitigate PuDHammer, and we have more details on adaptation. We have actually 2 adaptations. One of them is performance optimized, other one is area optimized, etc. And we also discuss the challenges of adapting PuDHammer. And we also, as I said, an area efficient crack solution and so on. So the paper is available on arXiv. You can find the paper over here, and let me conclude my talk. So here we extensively study the interaction between read disturbance and multiple row activation based processing using DRAM operations. And we categorize a lot DDR4 chips, 316 DDR4 chips from 4 major manufacturers. And we observe that PuDHammer significantly exacerbates the read disturbance vulnerability, and it bypasses in DRAM RowHammer mitigation. And we try to adapt PRAG to account for PuDHammer bit flips, and it still incurs almost 50% of performance overheads. And we hope that our findings guide system level and architecture solutions to enable read disturbance resilient future processing using DRAM systems. Thanks a lot for your attention. I'm happy to answer your questions if you have any. Yes. 93. Yeah. Mm-hmm. So here, why do we observe bit flips when the number of aggressors are 2? So I think you may know UTRR, Uncovering in DRAM TRR paper from 2021. Over there, they try to uncover TRR mechanisms and craft attacks. So basically, we try to use that. So with 10, it's like you're using 10 number of aggressors and you're not doing anything else. It's just you're hammering 10 of them. But with 2, what you do is that you have actually a decoy, like a dummy row that you actually try to tell a TRR that this is your aggressor. So leave me alone. This is your aggressor, and I'm going to do the hammering. So there's an effective access pattern that induces bit flips in that paper. So we just adapted that. And for 10, it still actually detects for others. But with 2, so I guess for example, in this TRR, what it does is that for refresh window, it just samples the highest one. And what we do is that in 3 of them, we hammer, and then in 1 of them, use the decoy. In 3 of them, hammer, 1 of them, use the decoy. When you do 10, you don't have that much of hammering. Like the budget is decreased that. So assume that you have 100 activation. With 2 number of aggressors, you can have 50 activation each, right? But with 10, you only have 10 activation for each. So the effectiveness also reduced. So that was the reason. Hope it's clear. Changes in with TRR or with TRR to without TRR. Okay. Yes. Yes. Yeah, because you don't have the budget of it. So basically, you have two access pattern, right? Either double-sided or single-sided. If you have 3 number of aggressors, you still have doubles. You can have only double-sided, or you can have like double-sided one here and here. So I think what we do is that we didn't optimize it. Basically, we use what UTRRs proposed, the most effective one. And when, as I said, when you go to a higher number of aggressors, the number of activation you can do in one aggressor reduces, right? Like if you have 2, as I said, you could activate them 50 for each. If you 3, it's 33. It's 4 is 25. And that was one of the reasons. But we didn't pursue it further, basically. It's just to basically show as a proof of concept, you can still induce, with it, let's say, not optimizing anything, you can still induce bit flips with TRR for RowHammer, because there's already a paper about it, actually multiple papers. And what we try to show is that with TRR, can we, like, things get much worse or not? So for COMRA, it's almost the same. What we are trying to show is that basically the Simon's effects is still there. That was the whole goal. But definitely you can optimize things, and then maybe you can get even not 60, maybe 100 or 1,000. Not sure about the 1,000, but probably you can get more. That was the reason. But great question, great catch. Thanks. Yeah. Let's go there. This one? So, again, what matters is that you do double-sided. With 2 rows, you can do double-sided. With 4 rows, you can do double-sided. One thing is that, so this is the row decoder circuitry works in a mysterious way. So you need to reverse engineer it, and you may not catch the rows that you will activate with 4. So for example, with 4, you will activate 3, 5, 7, and 9. But maybe with 2, you cannot activate 3 and 5. That's the thing of row decoder circuitry, basically. It's not, you cannot choose which rows to activate. You can just reverse engineer. You can map, if I have these 2 activations, that rows will be open. Basically, this is what we did. And we didn't test all the combinations. We test like some of them, we randomly select them, and we just run the test. So maybe if we test all of them, you will essentially, I mean, theoretically, you should see all of them the same. But what we do is that we randomly select the row groups that are simultaneously activated. But yeah, the fundamental observation is that it's much worse. That it's like 26 or 80. So all of theoretically, all of them should be the same, because what matters is that you double side. If you can catch that 2 rows, that like the victim rows, that is the most vulnerable one. If you can sandwich them with all of them, that should be the same, almost all of it. But it also depends, like, for example, as I said, this is a real DRAM chip that we play to imitate these operations. So there could be some differences, but I think the difference that we observe is that because of the selection of rows that we choose to do. Great question. Thanks. Any other questions? Okay, then that concludes my part, I guess. Do I have any more slides? No, that's it. Yes. And thanks a lot.
Yes. Well, I can be very fast, but yes, okay. I go on the mic. Okay, okay. Hey, I already included this self-introduction. Hi, I'm Nisa. I'm a PhD student in software research group at ETH Zurich. You all know that. And I'm broadly interested in computer architecture, but more so with memory system security, hardware security, safety, reliability, and performance. And I'm also doing some work on processing in memory architectures. And this is the sort of agenda for my part of the talk, but let's see how much we can cover. Basically, I will talk about understanding and mitigating Covert channel and side channel vulnerabilities introduced by RowHammer defenses, which is a paper that we published in Micro this year. Again, it was one of the papers that we recently presented, I guess, 2-3 weeks ago. And the second paper that I will likely cover is revisiting main memory-based covert and side channel attacks in the context of processing in memory architectures. And this paper was published in DSN again this year. And let's see if I can cover CoMeT, which is counting sketch-based role tracking to mitigate RowHammer at low cost, which was published in HPCA almost 2 years ago. And I also had ABACuS, which is all bank activation counters for scalable and low overhead RowHammer mitigations, which is again a sort of concurrent work to CoMeT. Okay, let's start with the first one, understanding and mitigating covert channel and side channel vulnerabilities introduced by RowHammer defenses. This is the outline of this part of the talk. I will start with the motivation and the problem. Modern systems are vulnerable to security attacks such as covert channel and side channel attacks that use the shared computing system to, for example, send messages between attacker processes or to spy on other applications that are concurrently running in the same computing system. And a set of these attacks exploit hardware structures that result in different execution time for a type of operation based on the input or the current state of the shared hardware structure. And this means that timing differences leak information. Now, let's take a closer look into these shared computing systems. Here we see a typical DRAM-based computing system with a CPU and a DRAM module connected over an off-chip link called the DRAM channel. And this DRAM module has multiple DRAM chips, and inside these DRAM chips, we have multiple DRAM banks, and inside them we have DRAM cells organized as two-dimensional arrays as rows and columns, and they are accessed in DRAM row granularity by being selected by word lines, and they are connected to the row buffer using these bit lines that you see here. Unfortunately, DRAM is vulnerable to read disturbance, which you learned so much about, and read disturbance breaks memory isolation. A prime example of this is RowHammer, where you open and close the same DRAM row many times that you end up with bit flips in nearby DRAM cells. And we call these bit flips RowHammer bit flips. And we refer to the hammered row as the aggressor row, and all other rows that end up with bit flips are called the victim rows. One way to mitigate read disturbance or read disturbance in DRAM is to preventively refresh potential victim rows before they experience bit flips. However, doing so requires tracking row activation counts of these aggressor rows to preventively refresh potential victim rows and to know when to do them. And to make things even worse, with technology not scaling, DRAM cells are getting smaller and getting closer to each other, which means that we observe significant reductions in the minimum hammer count to induce the first bit flip in the last decade, shown by these works. And thus, DRAM cells become increasingly more vulnerable to read disturbance, requiring low-cost defenses. To enable such defenses, recent DDR5 specifications introduced 2 new defense frameworks to mitigate these bit flips. The first one is called Pearl of Activation Counting, or PRAC, which Onur introduced yesterday a bit, and I will talk about that a bit more. It introduces Pearl of Activation counters to accurately track aggressor rows activation counts, and these counters are located inside the DRAM device. And the second framework is called Refresh Management, or RFM, which introduces a command to provide DRAM with the time to perform these preventive actions. The problem is the industry has already standardized these multiple RowHammer defenses to mitigate read disturbance bit flips. However, their full security implications are not known. So this brings us to the question, do industrial and academic RowHammer defenses introduce new covert and side channel vulnerabilities? And the answer is unfortunately yes. In this work, we make the key observation that preventive actions for these bit flips have two fundamental features that enable covert channels and side channels. First, these actions often result in high memory access latencies for regular memory requests, meaning that when DRAM is doing these preventive actions, which have high latency, such as this number, 1400 nanoseconds per track, all other requests need to wait for them to finish such that they experience higher memory access latencies. And the second feature is that a user can leverage memory access patterns to intentionally trigger a preventive action, such as an attacker can craft memory requests targeting the same DRAM row and cause DRAM and hammer that row and cause DRAM to perform these preventive actions. And as a result, again, all other workloads, all other memory requests experience higher memory access latencies. By using this key observation, we introduced LeakHammer, which is a new class of attacks that exploit RowHammer defense-induced memory latency differences. And LeakHammer's key idea is to first deterministically and intentionally impose observable latency overheads on requests with preventive actions, and accurately infer victims' memory access patterns that result in preventive actions by observing the system and the preventive actions that are happening in the system. We demonstrate LeakHammer with 3 case studies. First, we built 2 covert communication channels using PRAC and RFM, which are the latest 2 industry defense frameworks. And then we demonstrate a website fingerprinting attack that leaks which website is loaded by a victim user by just observing the preventive actions that are caused by the victim. Before talking about these case studies, I want to first talk about our evaluation methodology. Even though these defenses are standardized, they are not widely available in chips today. So this is why we use system simulations with Gen 5 integrated with cycle level DRAM simulator emulator 2. And we use these configurations to model a modern DRAM-based system. And all of these can be found in our GitHub repo, where we open source all our data and source code. Now let's talk about the PRAC-based covert channel attack. Before that, again, I will explain per-row activation counting as it is proposed in DDR5. Here we have a CPU with a DRAM module, and inside the DRAM module, we have many DRAM rows, and all of these DRAM rows, each of them have one activation counter, which accurately tracks the activation counts for that row. A PRAC-based defense works as follows. Let's say that we have an activation to row A. This defense increments the activation counter that corresponds to row A. And with each activation, we increment the same counter until a point that it reaches a predetermined threshold called backoff threshold. This means that this row now requires a preventive action to happen unless if we don't do that, we will end up with bit flips. And the DRAM module identifies this row as an aggressor row. And after that, the DRAM module sends a backoff signal back to the memory controller, saying that I need some time to do these preventive actions. And the memory controller responds with an RFM command, which allocates a fixed time for these preventive refreshes to happen. And during this time, DRAM becomes unavailable and performs these preventive actions and preventive refreshes. And after this period ends, the DRAM becomes available again, and the memory controller continues to send regular memory commands. And in order to exploit this PRAC for an attack, we first need to verify if we can observe PRAC-induced latencies by intentionally triggering it. And basically, we are trying to verify that we can observe these higher memory access latencies deterministically. And to do so, we start by allocating pages, let's say addresses A and B, in different DRAM rows of a DRAM bank. Our goal here is to use those 2 different pages to increment these activation counters and cause a backoff. And to do so, we first flush the first address from the caches such that we ensure the next accesses will go to the main memory instead of being served from the caches. And then we read that address and measure the access latency. And we, again, in the next step, we do the same step, the same operations for address B. By repeating these 2 steps together, we basically activate both rows and increment their counters, and we expect to see a backoff after a number of activation counts. So now let me show you the results. So here on the x-axis, we see the memory requests, 512 memory requests to be exact. And on the y-axis, we see the memory request latencies. And these are the results that we observed. We empirically categorize these request latencies that we observed from highs to the lows. We have backoffs. and then we have periodic refreshes, and then we have row buffer conflicts. And we observe that we can identify these backups as the highest peaks in this figure, which is consistent with the specification and can be distinguished from regular memory requests and operations such as refreshes and row buffer conflicts. And this experiment shows that PrEP creates a promising timing channel for us to build attacks on. Now let's see an overview of the Covert channel attack. Here we have a sender and a receiver process, and the sender wants to send this message using this shared DRAM bank. They start by allocating pages in different DRAM rows inside the same DRAM bank, and they agree on it, and they agree on transmission windows. And this means that in each transmission window, they know that only one bit will be transmitted. They also agree on an encoding, meaning that the message will be transmitted as a logic 1 meaning a backoff, a backoff meaning a logic 1, and no backoff will mean a logic 0 bit value. And after that, they can basically do the attack. So the receiver receives this message by executing a loop. And in this loop, it accesses its own DRAM row repeatedly and measures the time it takes to do these accesses. And at the end of the transmission window, the receiver will have a trace of these memory requests that will be similar to this one. And this then will be used to determine the bit value. And the sender transmits the message. Let's say that we want to transmit a logic 1 value with a backoff. So to do so, the sender accesses its own DRAM row at the same time as the receiver is accessing its own DRAM row. This results in basically activating two of these rows and to a point where they reach the threshold value. And the DRAM module sends a backoff signal at this point. And the receiver, at the time that we see this backoff, the receiver will measure a high latency indicating a backoff and can determine the bit value as a logic 1 value. To send a logic 0 value, the sender needs to cause no backoff. And to do so, the sender just sleeps throughout the transmission window. This means that the receiver is accessing this DRAM bank or this DRAM row alone, which means that we have a lot of row buffer hits, meaning that the counter value is not increased as much. And throughout the transmission window, we do not see any backoff. So the latency trade, something like this. This indicates no backoff has happened, and the receiver measures the bit value as the logic 0 value. And they repeat these steps to basically send the whole message bit by bit. We validate this proof of concept by sending a 40-bit message. Here on the x-axis, you see the transmission windows, and this message spells out micro. And on the y-axis, we see the number of backoffs detected by the receiver process. And these are the results. The background color here indicates the bit value that the sender intended to send. And as you can see, these are basically the same as consistent with the measurements of the receiver. So we conclude that the receiver successfully decodes the sender's message after all the message bits are transmitted. We also evaluate the channel capacity by sending a longer message, and we show that the attack achieves 39 kilobits per second raw bit rate. Next, we look at the impact of the noise in the system in the basically the channel capacity of this attack. To do so, we use the micro benchmark that causes backoffs with varying frequencies to simulate the system noise. And the results will be shown here. On the x-axis here, we see the noise intensity in terms of percentage, and the lowest level here is similar to basically 10x of a 4-core memory intensive workload, meaning that if you had 4-core memory intensive workloads, the amount of backups that they will generate is multiplied by 10 to get the lowest level of the noise. And as we go to the higher noise intensities, it becomes similar to having a memory performance attack that uses backups in the system. And basically, it is like a very high noise intensity value. On the primary y-axis, we will see the error probability. And on the secondary one, we will see the channel capacity. And these are the results. So we observe that at the lowest noise intensity level, the error probability is very low. And this is why the channel capacity is high, meaning that we can transmit most of the bits correctly. And as we go to the higher noise intensity values, the error probability increases because basically the receiver is measuring the noise backoffs and determining the bit values wrong. And this is why the channel capacity degrades. But again, this becomes a problem, meaning that the channel capacity is significantly reduced at a level that is similar to having a memory performance attack in the system, which you do not want in your system anyway. So we conclude that the PRAC-based cover channel attack maintains its capacity until very high noise intensity values. Next, we have RFM-based cover channel attack, but I will not go into the details of it in the interest of time. And if you're interested in that, please check our paper. The last case study is PRAC-based website fingerprinting attack. And in this attack vector, we have an attacker and a victim. And the victim loads a website using a web browser, and the attacker wants to determine which website is loaded by only observing its own memory request latencies. To do so, they use the shared DRAM module. And basically, in this attack vector, we do not need to collocate in the same DRAM bank because the backoffs that are caused, they affect the whole channel, meaning that we don't have the collocation requirement. And in order to do this attack, the attacker first needs to understand or figure out how to fingerprint. And to do so, the attacker first allocates multiple test rows to avoid triggering backoffs while observing. So we are trying to cause no interference or as little as possible interference with the victim. And after that, the attacker uses these test rows and accesses them continuously and measures access latencies to attack backoffs. This is similar to what the receiver did in the other case studies. And after that, basically the attacker can create a fingerprint of this website by only using the timestamps of the backoffs. And in this example picture here, each line here corresponds to one backoff that is detected in the system. To prepare for the attack, the attacker creates a database of fingerprints by getting fingerprints of many websites with multiple instances, and basically has a lot of fingerprints to know what different websites look like. And after that, we can launch the attack. So the victim loads a website, and the attacker gets a fingerprint at the same time and compares it with the web database and determines the website that is accessed. And in this example, the website is YouTube. And we evaluated this proof of concept by first collecting backoff fingerprints of a website by loading it with a browser and getting a backoff trace. And we did this for 40 most visited websites, and we get a lot of instances of these websites to basically get a lot of data. And we used the machine learning approach to classify these websites. We only use simple and lightweight machine learning models like decision trees, random forest, and so on. And now I will show you the test accuracy results. On the x-axis here, we see the ML models. One thing to note here is that these models are predicting or classifying on their own. They're not making a prediction altogether. So on the y-axis, we see the test accuracy that is coming from that. And here are the results. The red line here represents the accuracy of the random guess, and it is very low because we have many websites. We basically observe that using backoff-based fingerprints, a classical machine learning model, or many of them can classify websites with up to 75% accuracy. Now, what we showed is that the leak hammer can have significant implications on system security. Now let's discuss how to mitigate it. We proposed 3 countermeasures against leak hammer. The first one is called fixed rate RFM, which eliminates leak hammer by decoupling preventive actions from memory access patterns of concurrently running applications. And the second one is randomly initialized activation counters, which reduces channel capacity with a randomization method. The last one is called bank level PRAC, which performs bank level preventive actions to limit the attack scope to that of existing DRAM-based attacks. I will describe the first one again in the interest of time. So fixed rate RFM periodically performs a preventive action. Periodic here means in time, which is independent from the memory access patterns that we have. And we configure this defense to basically perform these preventive actions in a period or in a frequency that is secure against RowHammer, which we have the security proof for that in our paper. If we employ fixed rate RFM, this means that the standard cannot cause preventive actions intentionally to send messages, and an attacker cannot observe a victim's memory access patterns that lead to a preventive action because all preventive actions happen at a fixed rate without any impact coming from the memory access patterns of the applications. And we evaluate all of these countermeasures that we propose across 64 core workloads from spec benchmarks. And on the x-axis here, we see the RowHammer thresholds from 1K to much lower thresholds. And on the y-axis, we see the normalized weighted speedup. The weighted speedup here is normalized to a baseline with no RowHammer mitigation. And we evaluate a couple of different designs. The first two defenses are not secure against leak hammer. They're PRAG and RFM. But they are secure against RowHammer. Next, we have the randomization method that reduces the capacity. Next, we have fixed rate RFM, which is secure against leaky hammer. And lastly, we have the bank level PRAG, which limits the attack scope. And these are the results. So we observe that fixed rate RFM mitigates leaky hammer and performs similar to these insecure baselines for near future RowHammer threshold values. And as we go to the lower RowHammer thresholds, its performance overhead increases significantly. And at these threshold values, other countermeasures that limit the attack scope or limit the channel capacity, they have lower performance overheads. We have even more content in the paper, starting with more details of leak hammer, operational details, or countermeasure details, and so on. And we have more results and analyses, such as leaky hammer with other RowHammer mitigations, impact of real workloads on leaky hammer in terms of noise, and sensitivity studies, and so on. So these can be found in our paper. LeakHammer is open source and artifact evaluated, and if you want to check our source code and data, you can do so with this link. Now let me conclude this part of the talk. In this work, we introduced LeakHammer, which is a new class of timing attacks that exploit RowHammer defense-induced memory latency differences. We systematically analyzed two latest industrial defenses to RowHammer and built two covered communication channels and demonstrated a website fingerprinting attack that identifies visited websites with high accuracy. We proposed and evaluated three countermeasures, one of them completely mitigating LeakHammer with low performance overhead for in near future DRAM-based systems. And we showed that in systems that are highly RowHammer vulnerable, countermeasures that reduce the channel capacity have or limit the attack scope have lower performance overheads. And this concludes this paper. I would be happy to take any questions. Maybe everyone is very tired. Yes. So right now, what we have, basically the real DRAM chips that we have do not have PRAG yet. But the specification includes them. And we assume that a lot of people in the area also assume that PRAG will be the mitigation that will be implemented in many DRAM chips in near future. So I would love to test them, but we basically don't have the real chips with these mitigations, these exact mitigations right now. Yes. So basically, in terms of like side channel knowledge that you get, you can understand a concurrently running application has a memory access pattern that triggers it, meaning that you know if someone accessed a DRAM row enough times to cause this. And what we show is that this correlates with application behavior such that when your browser is loading a website, it has a different basically behavior in terms of backoffs. So different websites cause backoffs in different ways, maybe in different numbers, maybe in different frequencies, such that you can correlate it with the knowledge of which website is loaded. It is also possible, it might be possible, and other works also like sort of explore that direction. If you have more attacker capabilities, such as you collocate in the same DRAM row with the victim, meaning that you have a page in the same DRAM row that a victim has a page in. So you don't share actual data, but you have access to the same DRAM row. You can understand how many times that row was activated before you activate it. So you can get the activation counter value. So that's also like one scenario that we discuss in the paper, which might leak more information about a victim process accessing one specific page X times. So that could be used to, for example, leak keys, cryptographic keys, and so on. Yes. Yes. Mhm. So basically, it's not like a requirement to have more information, but you're limited by the data set that you have. So what we have is 40 websites, and if the victim is accessing another page that is not in our database, we won't be able to guess it. That's like the requirement that we have. That is like a closed world sort of attack, as it is called in the security area. And other website fingerprinting attacks also assume similar, basically, setups. Oh, maybe I can also mention that. This is also somewhat useful if you have like one target malicious website you have in mind. You can get like a fingerprint for that specifically, and it might be still useful to guess if the victim is specifically accessing that website. Like that changes the problem a bit. So that's another attack vector that this might be useful for. Mhm. Yeah, I think it would be interesting to check and see if one can do open world attacks where you can access any other website and still get like a meaningful measurement coming out of them. Please. So the content has an impact on the fingerprint that we generate because we basically, the memory access pattern can be affected by the content type if it's like a video-based website and so on. We saw some similarities, but they were not strong enough to make like some insights or observations from. But I think it would be interesting to look more into it and basically sort of target that separately from this work. What was interesting is that a lot of these websites, for example, we had Reddit in one of these, basically in the set of websites that we looked into, and the content type depends on when you open the website. So you can get a video, you can get like different posts with texts and so on, and it was changing, and we were still be able to get a fingerprint that we can accurately guess. So it's not just the content type, but the website itself also has maybe some different memory access patterns, but that's like a combination of two that you get with the fingerprint. Okay, if there are no other questions, I will quickly go to the next one. Sure.